The Lockheed YF-12 represented a pinnacle of American aerospace engineering, boasting Mach 3+ capability and high-altitude interception potential. Developed and produced by Lockheed Corporation, this interceptor emerged during the late 1950s and early 1960s as a candidate to replace the F-106 Delta Dart interceptor within the United States Air Force. President Lyndon B. Johnson publicly disclosed the existence of the YF-12 on February 24, 1964, primarily to provide a cover story for the CIA-operated A-12 fleet, which closely resembled the newly revealed prototype. Despite undergoing rigorous flight evaluations by the USAF during the 1960s, operational deployment of the YF-12 was thwarted by funding constraints, compounded by the difficulties of the Vietnam War and other military imperatives. Nevertheless, it secured and maintained speed and altitude records exceeding 2,000 miles per hour, 3,200 kilometers an hour, and soaring beyond 80,000 feet, 24,000 meters, subsequently eclipsed by its successor, the SR-71 Blackbird. Remarkably, the YF-12 holds the distinction of being the world's largest, heaviest, and fastest crewed interceptor. After its retirement from USAF service, the YF-12 found new life as a research platform for NASA, contributing to advancements in supersonic aircraft control systems. Originating from the Long Range Interceptor Experimental LRIX initiative, which initially considered the North American XF-108 Rapier, the YF-12's genesis, intertwined with Lockheed's A-12 reconnaissance program, was overseen by the CIA under the Oxcart program. Under the visionary leadership of Kelly Johnson at Lockheed Skunk Works, the YF-12 emerged as a derivative of the A-12, designated as the AF-12, and subsequently configured as the YF-12A interceptor. The transformation of the A-12 reconnaissance aircraft into the YF-12A interceptor involved several key modifications, chiefly centered around accommodating the formidable Hughes AN/ASG-18 fire control radar originally intended for the XF-108 interceptor. The A-12's nose underwent alterations, including the reduction of the chines to integrate the large radar, along with embedding two infrared search and track sensors into the chine leading edge. Additionally, a second cockpit was installed to house a crew member responsible for operating the fire control radar for the air-to-air missile system. These modifications significantly altered the aircraft's aerodynamics, necessitating the addition of ventral fins under the fuselage and engine nacelles to maintain stability. Moreover, 3 of the A-12's 4 bays were repurposed to accommodate Hughes AIM-47 Falcon GAR-9 missiles, while 1 bay was dedicated to fire control equipment. The YF-12A's maiden flight took place on August 7, 1963, although its existence was not publicly acknowledged until President Lyndon B. Johnson's announcement on February 24, 1964. This revelation served to divert attention from the still classified A-12 program. The YF-12A was showcased to the public for the first time on September 30, 1964 at Edwards Air Force Base. Despite the promising performance of the YF-12A and the subsequent order of 93 F-12B aircraft for the Air Defense Command, the program faced setbacks due to funding constraints driven by the escalating costs of the Vietnam War. Secretary of Defense Robert McNamara withheld funding for 3 consecutive years, leading to the cancellation of the F-12B program in January 1968. During flight tests, the YF-12A set impressive speed and altitude records, reaching 2,070.101 miles per hour, 3,331.505 kilometers an hour, and 80,257.86 feet, 24,462.6 meters, respectively, on May 1, 1965. The unique weapon system of the YF-12A also demonstrated promise, with 6 successful firings of the AIM-47 missiles completed. Although one missile failed due to gyro malfunction, the remaining missiles showcased their effectiveness, including a remarkable hit on a JQ-B-47E target drone at Mach 3.2 and an altitude of 74,000 feet, 23,000 meters, resulting in a direct hit and significant damage. The YF-12 program faced significant challenges despite its successes, particularly in securing further funding and addressing control issues that affected both engine performance and physical aircraft control. Secretary of Defense McNamara redirected funding from the YF-12 program to the F-106X program, which faced difficulties and was less successful. Despite this setback, developments from the YF-12 program found applications in subsequent projects. The AIM-47 Falcon missile, proven successful during YF-12 testing, underwent enhancements to become the AIM-54 Phoenix missile used on the F-14 Tomcat. Additionally, upgrades to the AN/ASG-18 radar resulted in the AN/AWG-9 and APG-71 systems, which provided improved tracking capabilities for multiple targets. Jim Irwin, one of the Air Force test pilots involved in the YF-12 program, transitioned to become a NASA astronaut and famously walked on the moon. Although the production of the F-12B was cancelled, the YF-12 aircraft continued to serve both the USAF and NASA as research aircraft for many years. NASA conducted tests to address various engineering challenges, including engine inlet performance, boundary layer noise, heat transfer under high Mach conditions, and altitude hold at supersonic speeds. These tests were crucial for advancing the understanding of supersonic flight. The YF-12 and the SR-71 initially faced control issues, but wind tunnel testing and research flights led to the development of computer systems that significantly improved performance and stability. The implementation of systems like the Central Airborne Performance Analyzer and the Cooperative Airframe Propulsion Control System played crucial roles in enhancing the control of supersonic aircraft during flight, addressing issues such as engine unstarts and improving overall stability and performance. The challenges of controlling aircraft at such high speeds were significant, with even minor changes in direction leading to substantial deviations in position, often accompanied by severe temperature and pressure changes. The implementation of the Cooperative Airframe Propulsion Control System played a crucial role in mitigating these deviations, reducing them by a factor of 10. These improvements not only enhanced the stability and control of the aircraft, but also increased the range of the SR-71 by 7%, demonstrating the effectiveness of the system in optimizing performance. Unfortunately, the YF-12A program experienced losses during its operational lifespan. One of the aircraft, designated AF serial number 606934, was damaged beyond repair in a landing mishap at Edwards Air Force Base on the 14th of August 1966. Another YF-12A, AF serial number 606936, was lost on the 24th of June 1971 due to an in-flight fire caused by a failed fuel line. Fortunately, both pilots ejected safely, averting a potential disaster. The sole surviving YF-12A, designated AF serial number 606935, was recalled from storage in 1969 for a joint investigation by the USAF and NASA into supersonic cruise technology. It was subsequently transferred to the National Museum of the United States Air Force at Wright-Patterson Air Force Base near Dayton, Ohio, where it remains as a testament to the pioneering era of high-speed, high-altitude flight research. The North American X-15 was a marvel of the skies, bold, sleek, and faster than any other manned aircraft in history. Despite its maiden flight over 6 decades ago, it still holds the title of the swiftest manned aircraft ever to grace the heavens. Resembling a bullet more than a conventional plane, this rocket-powered marvel completed an impressive 199 test flights spanning 9 years, commencing in 1959. Its capabilities extended to reaching the fringes of space before gradually gliding back to Earth, gathering invaluable data that would shape the future design of American spacecraft, including NASA's iconic space shuttles. A select group of only 12 elite pilots, among them the legendary Neil Armstrong, had the privilege of piloting this extraordinary craft, paving the way for historic achievements like the 1969 moon landing. Christian Geltzer, chief historian at NASA's Armstrong Flight Research Center, once described the X-15 as the pinnacle of aviation aspiration, a thrilling blend of speed, excitement, and apprehension that no other aircraft has matched since. The X-Series, encompassing over 60 experimental aircraft developed by various US government agencies post-World War II, was a testament to the nation's relentless pursuit of aerospace innovation. These groundbreaking machines, epitomized by the X-15, consistently pushed the boundaries of what was considered possible. When the X-15 project took flight in 1952, it set its sights on a lofty goal, shattering the existing airspeed record, which at the time hovered just below 700 miles per hour. The primary objective of the X-15 was to achieve the remarkable feat of reaching Mach 5, equivalent to 5 times the speed of sound, or nearly 4,000 miles per hour. This endeavour posed immense challenges, remarked Geltzer. Not only did the aircraft have to attain such staggering speeds, but also had to soar to an altitude of 250,000 feet, surpassing any previous aircraft's operational ceiling. It was an exceedingly ambitious goal. Led by the US Air Force and the precursor to NASA, the National Advisory Committee for Aeronautics, NACA, the project aimed not only to gather scientific and flight dynamics data, but also operated against the backdrop of the Cold War, driving a sense of urgency and motivation behind the research efforts. Unlike conventional aircraft, the X-15 resembled more of a rocket with a cockpit, necessitating a unique launch procedure. Instead of taking off from a runway, it relied on being carried aloft by a mothership, specifically a specially modified B-52 bomber. With the X-15 nestled beneath its wing, the B-52 would depart from Edwards Air Force Base in Southern California, embarking on a trajectory towards Nevada or Utah. Upon reaching the designated release point, typically at an altitude exceeding 45,000 feet and a speed surpassing 600 miles per hour, the X-15 will be set free to commence its ascent into the heavens. Only then would the X-15 pilot ignite the rocket engine, propelling the aircraft out of Earth's atmosphere and into the realm of space. The propulsion system, comprising a blend of ammonia and liquid oxygen, provided a mere 2 minutes of thrust, subjecting the pilot to a tumultuous and challenging journey. It flew aerodynamically like a normal airplane, but it climbed like nobody's business, said Geltzer. Milt Thompson, who was one of the pilots, said that it was the only airplane he ever flew in which he was glad when the engine quit. Once the X-15 reached its target altitude, which soared as high as 354,200 feet, approximately 10 times the cruising altitude of a typical commercial airliner, the pilots embarked on a series of groundbreaking experiments in this uncharted realm, contributing invaluable data to our understanding of hypersonic flight. Much of the X-15's engineering was tailored to accommodate high-altitude operations, where the atmosphere becomes so tenuous that traditional aerodynamic control surfaces become ineffective. To address this challenge, the X-15 was outfitted with a pioneering reaction control system reminiscent of those later employed by space shuttles and the International Space Station. This system expelled bursts of hydrogen peroxide, a highly concentrated oxygenated form of water, generating modest thrust, capable of maneuvering the aircraft within the rarefied upper atmosphere. Travelling at velocities reaching thousands of miles per hour, the outer surface of the X-15 endured intense heating caused by aerodynamic friction. To withstand these extreme conditions, the aircraft's skin was crafted from a specialized nickel-chromium alloy known as Inconel X. The aircraft heated up to 1,200 degrees Fahrenheit, Geltzer said, and the pilots could hear it expand behind them. Landing the X-15 wasn't easy. From the moment it ran out of fuel or the pilot turned off the engine, it was a glider. A very heavy, very fast glider with very small wings, so not even a great glider. At that point, the pilot only had speed and altitude to exchange for reaching his destination, said Geltzer. Adding to the challenges, the X-15 faced limitations in its landing gear configuration. With a front wheel lacking steering capabilities and main landing gear featuring only skids, retractable steel beams that slid along the landing surface, a traditional tarmac runway was out of the question. Consequently, the aircraft was compelled to land on a dry lake bed. After each flight, the aircraft returned to base transformed, bearing witness to the punishing conditions it endured. The heat had left its mark, with visible burns and holes, Geltzer noted. While conventional aircraft typically execute final landing approaches at speeds below 200 miles an hour, the X-15 operated under vastly different circumstances. It commenced its descent from altitudes of up to 20,000 feet, hurtling towards the ground at supersonic speeds exceeding 1,500 miles per hour, an experience far removed from the norm for most pilots. Regrettably, not every flight concluded without incident. This was an experimental aircraft, and things went wrong almost every single slide. The remarkable feat is that the pilots consistently managed to bring the aircraft back despite the challenges, Geltzer remarked. Of the nearly 200 flights undertaken, only 2 ended in crash landings, tragically resulting in the loss of pilot Michael Adams. On November 15, 1967, Adams encountered a spin during re-entry, unable to stabilize the aircraft, which ultimately disintegrated in mid-air. The inherent dangers associated with piloting this hybrid aircraft, part plane and part spaceship, partly explain why the X-15's records remain unchallenged by modern engineering. Moreover, it served as a crucial precursor to the space program, which aspired to achievements beyond mere speed. Yet the X-15's legacy endures as one of the most triumphant flight research programs in history. Over its 9-year tenure, it amassed invaluable data on high-speed flight, space re-entry, and human physiology. In 1967, pilot Pete Knight set a record speed of 4,520 miles per hour, equivalent to Mach 6.7. During one of his 7 X-15 flights, Armstrong demonstrated the problem-solving acumen that would later propel him to command Apollo 11. In 1962, he embarked on a flight reaching 205,000 feet, a Mach 3.8, Geltzer recounted. On the return journey, he encountered an unprecedented bounce off the upper atmosphere at around 90,000 feet, akin to skipping a stone. Despite losing power and finding himself over a Los Angeles suburb, Armstrong skillfully guided the aircraft back, executing a successful landing on Rogers Dry Lake. It remains the longest X-15 flight on record. The North American XB-70 Valkyrie indeed represented a bold and ambitious leap forward in strategic bomber design during the Cold War era. With its ability to fly at supersonic speeds and operate at high altitudes, the Valkyrie embodied the pursuit of technological superiority and strategic deterrence. Its impressive performance capabilities, including a top speed exceeding Mach 3 and a cruising altitude of 70,000 feet, set it apart from conventional bombers of its time. Designed to carry a substantial payload of nuclear weapons over long distances at high speeds, the XB-70 promised unparalleled strategic striking power. However, the XB-70 also faced significant challenges and limitations. Its immense size and weight, coupled with the complexities of its advanced design, posed engineering and operational hurdles. Additionally, evolving military doctrines and advancements in missile technology rendered the high-altitude, high-speed bomber concept less relevant over time. Despite its status as a technological marvel and a symbol of aerospace innovation, the XB-70 ultimately fell victim to changing strategic priorities and the shifting landscape of aerial warfare. While its legacy lives on as a testament to the ambitious spirit of Cold War-era aviation, the Valkyrie's operational career was short-lived and only a handful of prototypes were ever built. The engineering innovations incorporated into the XB-70 Valkyrie were indeed groundbreaking and aimed at maximizing its performance capabilities. The 6 powerful General Electric YJ93 turbojet engines, each generating 28,800 pounds of thrust, provided the necessary propulsion for achieving and sustaining supersonic speeds. The use of afterburners, particularly effective at high speeds, enabled efficient supersonic cruise, albeit at the expense of fuel consumption. The utilization of fuel for cooling, a technique also employed in the SR-71 Blackbird, exemplifies the innovative approaches adopted to address the extreme heat generated during high-speed flight. By circulating fuel through the aircraft's structure, heat absorption and dissipation were managed, contributing to the aircraft's ability to withstand the rigors of supersonic travel. The delta wings, with their inherent aerodynamic advantages at supersonic velocities, were further optimized with adjustable wingtips to enhance the aircraft's performance characteristics. This, combined with a sophisticated wedge-shaped air intake and other design features, allowed the XB-70 to exploit its own shockwave for reduced drag and increased lift, facilitating efficient flight at high speeds and altitudes. Moreover, the use of advanced materials like titanium and brazed stainless steel honeycombs contributed to the aircraft's structural integrity and overall weight reduction, essential for achieving optimal performance in extreme flight conditions. These cutting-edge materials represented a significant leap forward in aerospace technology, enabling the XB-70 to push the boundaries of speed and altitude like never before. The XB-70 Valkyrie's capabilities indeed surpassed those of contemporary aircraft, positioning it as an unparalleled asset in the realm of strategic aviation. However, the emergence of advanced surface-to-air missile systems, particularly the Soviet S-75 Dvina, posed a formidable threat that undermined the XB-70's strategic relevance. The S-75 Dvina's ability to match the XB-70's speed and altitude performance rendered traditional manned bombers increasingly vulnerable, prompting a shift in military strategy towards intercontinental ballistic missiles, ICBMs, as a more effective deterrent. The evolving landscape of military technology and strategic priorities led to the cancellation of the XB-70 program as a defense project in 1961. Nevertheless, the XB-70 found a new role within NASA's research initiatives, leveraging its exceptional speed and altitude capabilities to support the development of a potential American supersonic transport. NASA's utilization of the XB-70 for testing and experimentation underscored its enduring significance as a platform for advancing aerospace innovation beyond its original military applications. Furthermore, NASA's involvement in refining the XB-70 design, particularly with enhancements to stability and high-speed performance, exemplified the aircraft's adaptability and versatility in addressing diverse aviation challenges. While the XB-70's military aspirations may have been curtailed by shifting strategic imperatives, its legacy endured through its contributions to pioneering research endeavors aimed at shaping the future of supersonic flight. The tragic mid-air collision involving the second XB-70 Valkyrie during a photo shoot in 1966 marked a somber chapter in the aircraft's history. The loss of the Valkyrie's vertical stabilizers and the subsequent unrecoverable roll underscored the inherent risks associated with high-speed flight testing and aerial maneuvers. As the aviation landscape evolved, with advancements such as the YF-12 and the SR-71 surpassing the capabilities of the XB-70, the Valkyrie's role became increasingly marginalized. The loss of the more capable second XB-70 further diminished its relevance in comparison to the more advanced research capabilities offered by other aircraft. The retirement of the sole remaining XB-70 on February 4, 1969, symbolized the end of an era for the groundbreaking aircraft. Despite its limited flight hours, the XB-70 left an indelible mark on aviation history, serving as a testament to the ingenuity and ambition of aerospace engineers and the pursuit of pushing the boundaries of flight. The XB-70 Valkyrie's presence at the National Museum of the US Air Force indeed commands attention and stands as a testament to its monumental significance in aviation history. Its imposing size and distinctive angular design make it a focal point in the museum's Research and Development Gallery, overshadowing even other remarkable prototype aircraft. With its futuristic appearance characterized by sharp edges and sleek lines, the Valkyrie represents a vision of aviation that was ahead of its time. Its design language, dominated by right angles and razor edges, remains unparalleled, evoking a sense of innovation and progress. Despite its relatively short operational lifespan and absence of combat engagements, the Valkyrie's impact on aircraft design and technology cannot be overstated. It served as a precursor to future developments in aviation, influencing the designs of subsequent aircraft, particularly in the realm of supersonic transport. Indeed, the legacy of the XB-70 extends beyond its own existence, as multiple companies drew inspiration from its design principles when developing their own supersonic transport concepts. This legacy solidifies the XB-70 Valkyrie's place in aviation history as a pioneering aircraft that provided glimpses of the future of flight. The XB-70 Valkyrie's influence extends beyond its direct contemporaries, shaping the trajectory of aviation development in both the United States and the Soviet Union. The B-1 Lancer, with its swept-wing design and supersonic capabilities, bears echoes of the Valkyrie's shape, demonstrating how the XB-70's legacy lived on in subsequent aircraft designs. In response to the perceived threat posed by the XB-70, the Soviets developed the MiG-25, one of the fastest interceptors ever built. While the MiG-25 had its flaws, its successor, the MiG-31, remains in service to this day, underscoring the enduring impact of the XB-70 on global military aviation. The XB-70 Valkyrie stands as a quintessential symbol of early Cold War aviation, representing a bold and ambitious endeavor to push the boundaries of performance and technology. Despite its remarkable speed and advanced design, the XB-70 ultimately struggled to remain relevant in an evolving strategic landscape. In contrast, more versatile aircraft designs from the same era, such as the B-52 Stratofortesss, have endured and adapted to changing military needs, highlighting the challenges faced by revolutionary but specialized platforms like the XB-70. Nevertheless, the XB-70 Valkyrie remains a remarkable artifact of the jet age, offering a tantalizing glimpse into the futuristic vision of aviation promised in the 1950s. Its legacy continues to inspire awe and admiration for its groundbreaking design and ambitious aspirations. NASA achieved a significant milestone in aviation by successfully conducting the first and second flights of a scramjet-powered aircraft at hypersonic speeds, exceeding Mach 5, or 5 times the speed of sound.
Unlike conventional rockets that must carry its own oxygen to operate, scramjets are air breathers that obtain oxygen from the air in which it's flying, and this characteristic allows for much more airplane-like operations with increased safety, affordability, and flexibility.
The NASA Hyper-X program, spanning 8 years with an investment of around $230 million, represented a bold initiative in research, pushing the boundaries of what had been previously attempted. The successful March 2004 flight marked the first instance of an air-breathing engine-powered vehicle achieving hypersonic velocities. The intricate process of rocket propulsion, followed by scramjet operation, presented a series of technical challenges, all of which needed to be meticulously addressed for mission success. Despite thorough analyses and design optimizations aimed at mitigating risks, some residual risk remained inherent to the program. The Hyper-X Research Initiative began in 1996 with conceptual development and experimentation in wind tunnel environments. 3 unpiloted X-43A research aircraft were built. Each of the lifting body vehicles, measuring 12 feet in length and 5 feet in width, was designed for a single flight without recovery. While visually identical, these vehicles were engineered with subtle variations to simulate different engine configurations, typically corresponding to various Mach numbers. The initial 2 vehicles were optimized for flight at Mach 7, while the third was tailored for Mach 10 velocities. Operating at such velocities, the four-body shape of the vehicle functioned akin to pistons in an engine, compressing air as fuel was injected for combustion. The X-43A utilized gaseous hydrogen as its fuel source.
The ultimate goal of hypersonics really is twofold. One is to reduce the cost for access to space. Routinely getting to space with this type of technology or using this technology, an operational space access vehicle is a goal. The second goal, and probably one that's farther out, granted, but maybe 100 years out, But hypersonic commercial travel, I think, can be a reality someday and anywhere in the globe in just a few hours.
Following an unsuccessful launch attempt in June 2001 due to booster rocket malfunction, subsequent flights in March and November 2004 achieved remarkable success, breaking speed records. In March 2004, the X-43A attained a velocity of Mach 6.8, shattering the previous record for air-breathing vehicles. During its final flight at nearly Mach 10, the X-43A reached a speed of 6,755 miles an hour at an altitude of 110,000 feet, establishing a new world speed record for air-breathing vehicles. The Mach 10 vehicle was equipped with enhanced thermal protection, including the integration of carbon-carbon composite material on the leading edges of its vertical fins to withstand higher temperatures. Both flights commenced with the B-52B aircraft transporting the stack to a predetermined location over the Pacific Ocean, 50 miles west of the Southern California coast. The release altitude from the B-52B was consistent at 40,000 feet for both successful flights, from which point the booster propelled each research vehicle to its designated test altitude and velocity. Aside from variations in altitude, speed and distance covered, the flight profile of the Mach 10 mission mirrored that of the Mach 7 flight. Following separation from the booster, the Mach 10 research vehicle autonomously flew according to pre-programmed commands. Separation from the booster was facilitated by two small pistons. Shortly thereafter, the Scramjet engine operated for approximately 10 seconds, yielding substantial and unique flight data for an integrated Scramjet system. Throughout both flights, the engine's thrust closely matched its design specifications, enabling acceleration during the Mach 7 flight and sustained cruising at constant velocity during the Mach 10 flight. Upon completion of the Scramjet engine test, each vehicle transitioned into a high-speed maneuvering glide, gathering nearly 10 minutes of hypersonic aerodynamic data en route to a designated mission completion point. For the Mach 7 flight, this point was located approximately 450 miles west, while for the Mach 10 flight, it extended to 850 miles west, within the Naval Air Warfare Center Weapons Division Sea range off the southern coast of California. As planned, both vehicles descended into the ocean upon completion of their missions without any recovery efforts undertaken. The achievements of reaching Mach 6.8 and Mach 9.6 have been officially recognized by Guinness World Records, appearing on their website in the 2006 edition of their record book. The inaugural flight attempt of the X-43A took place in June 2001. However, it was unsuccessful due to booster failure, leading to its premature termination. Consequently, the research vehicle didn't undergo testing as it did not reach the required test conditions. Although no single contributing factor was found, the root cause of the problem was identified as the booster's flight control system. The booster's failure stemmed from inaccuracies in design models, which had overestimated the flight control system's capability to function within anticipated flight conditions. The HyperX program has played a pivotal role in pushing the boundaries of air-breathing flight, notably achieving the milestone of flying a scramjet-powered aircraft at hypersonic speeds for the first time. Various measures were implemented in response to the identified issues. These included conducting wind tunnel tests to gather data aimed at reducing atmospheric loads on the booster's control surfaces, enhancing booster fin actuators to better withstand aerodynamic forces, and adjusting propellant levels in the Pegasus booster to facilitate launches at the standard altitude of 40,000 feet, as opposed to the lower altitude of 23,000 feet utilized during the initial flight. A ramjet engine functions by combusting fuel in a stream of air compressed by the aircraft's forward speed, in contrast to conventional jet engines, where the compressor section compresses the air. Ramjets typically operate within the Mach 3 to Mach 6 range. Scramjets represent an advancement of ramjet technology, maintaining supersonic airflow through the engine. Envisaged applications for scramjet-powered vehicles extend to speeds exceeding Mach 15. While ground tests of scramjet combustors have demonstrated this potential, flight tests have yet to surpass the achievement of the Mach 9.6 flight attained by the X-43A. The HyperX program, managed by the Aeronautics Research Mission Directorate in Washington, was conducted jointly by the Langley Research Center in Hampton, Virginia, and the Dryden, now Armstrong, Flight Research Center in Edwards, California. Langley served as the lead center, spearheading the development of hypersonic technology. Dryden's responsibilities encompassed flight research, hardware integration, and testing. NASA's Aeronautics Research Mission Directorate is dedicated to advancing tools and technologies that can revolutionize air transportation operations, aircraft design, and manufacturing processes, and enhance the safety of the nation's air transportation system. The experimental X-51A Wave Rider serves as an unmanned autonomous hypersonic flight test demonstrator powered by a supersonic combustion ramjet Scramjet engine commissioned by the U.S. Air Force. Launched from an airborne B-52 Stratofortesss bomber, the X-51A comprises a stack approximately 25 feet in length, incorporating a modified solid rocket booster sourced from an Army tactical missile, an interstage connection, and the X-51A cruiser itself. The cruiser, nearly devoid of wings, derives its moniker Wave Rider from its unique design feature of riding its own shockwave. This distinctive aircraft boasts small controllable fins and houses the core component, a Pratt & Whitney Rocketdyne SJY-61 scramjet engine engineered to burn JP-7 jet fuel. Boeing's Phantom Works spearheaded the overall air vehicle design, assembly and testing, employing standard aerospace materials such as aluminum, steel, Inconel and titanium, supplemented by carbon-carbon composites for leading edges of fins and cowls. To withstand the intense thermal conditions, the X-51A integrates a silica-based thermal protection system developed by Boeing alongside reusable insulation tiles akin to those utilized on NASA Space Shuttle orbiters. The Air Force commissioned the construction of 4 X-51As, emphasizing the program's role as a technology demonstrator rather than as a prototype for a specific weapons system. Its primary objective is to advance hypersonic weaponry, intelligence, surveillance, reconnaissance capabilities, and enhance future access to space. The ability of scramjets to utilize atmospheric oxygen negates the need for large onboard oxidizer tanks, typical of conventional rockets, promising more efficient payload launches into orbit. Alongside scalable scramjet propulsion, the X-51A will showcase advancements in thermal protection systems materials, airframe and engine integration, and high-speed stability and control. Representing a significant reinvestment in hypersonic flight, the X-51A program stands as a pivotal milestone for the Air Force, echoing the pioneering spirit of the rocket-powered X-15 program that preceded it by half a century. Air Force officials foresee the X-51A program as a pivotal platform for acquiring the essential knowledge needed to propel future advancements in space access and hypersonic weaponry. The program's potential for hypersonic speeds, such as covering 600 nautical miles in just 10 minutes, promises rapid and precise engagement of distant targets, a capability with transformative implications. A collaborative endeavor between the Air Force Research Laboratory, the Defense Advanced Research Projects Agency, DARPA, and industry partners, the Boeing Company and Pratt & Whitney Rocketdyne, the X-51A program is managed by the Air Force Research Laboratory Propulsion Directorate at Wright-Patterson Air Force Base, Ohio. Hypersonic flight, commencing at Mach 5, presents distinctive technical hurdles involving extreme heat and pressure, rendering traditional turbine engines impractical. Generating thrust with a scramjet engine is likened to maintaining a flame in a hurricane, an analogy underscoring the formidable challenges faced by program officials. The Air Force intends to execute identical flight profiles for each X-51A, akin to the operational approach of the X-15. Following this same deployment method as its predecessor, the X-51A is hoisted aloft by a B-52 mothership from the Air Force Flight Test Center at Edwards Air Force Base, California. Upon reaching approximately 50,000 feet above the Pacific Ocean's Point Mugu Naval Air Warfare Center sea range, the solid rocket booster propels the X-51A to around Mach 4.5 for 30 seconds before detaching. Subsequently, the cruiser's scramjet engine initiates, distinguished by its minimal moving parts, initially burning ethylene and transitioning over a span of roughly 10 seconds to the JP7 jet fuel previously employed by the SR-71 Blackbird. Powered by its scramjet engine, the X-51A accelerates to approximately Mach 6 while ascending to nearly 70,000 feet. Hypersonic combustion generates intense heat, so routing the engine's own JP7 fuel will serve to both cool the engine and heat the fuel to optimum operating temperature for combustion. The X-51A's fuel load and flight profile facilitate a 240-second engine burn, during which extensive telemetry data on its systems is transmitted to orbiting aircraft and ground stations. As planned, the vehicle exhausts its fuel supply, ultimately splashing down into the Pacific Ocean, where it meets its preordained demise. Flight test vehicles are intentionally not recovered, a decision made by the X-51A development team from the outset to streamline costs and prioritize funding toward perfecting the vehicle's fuel-cooled scramjet engine. During flight, telemetry data is relayed to engineers stationed at Naval Air Station Point Mugu and Vandenberg Air Force Base, California, via a U.S. Navy P-3 Orion aircraft. This information is then forwarded to the Ridley Mission Control Center at Edwards Air Force Base, where it undergoes analysis. Conceived in 2004, the X-51A embarked on its inaugural captive carry flight on December 9, 2009, validating the B-52's performance and handling characteristics at high altitudes with the X-51 attached. Communication and telemetry systems were also tested during this flight, albeit with the vehicle remaining attached to the B-52's wing. The X-51A etched its name in the annals of aviation history during its maiden supersonic combustion ramjet-powered hypersonic flight on May 26, 2010, off the coast of Southern California. Demonstrating flawless performance, the scramjet propelled the vehicle to approximately Mach 5, or nearly 3,400 miles per hour, for nearly 200 seconds. Although telemetry remained normal for over 140 seconds, a decrease in thrust and acceleration occurred during the subsequent 30 seconds, followed by an anomaly resulting in a loss of telemetry. Consequently, flight controllers terminated the test and commanded the destruction of the vehicle. Despite the anomaly, the May 26 flight marked the inaugural use of a practical hydrocarbon-fueled scramjet in flight. Notably, this achievement surpassed the longest previous hypersonic scramjet flight test conducted by a NASA X-43 in 2004, which, although faster, lasted only about 12 seconds and employed less logistically supportable hydrogen fuel. Subsequent to an exhaustive analysis of flight data from the X-51A's maiden hypersonic flight, slight modifications are slated to reinforce the rear seal area near the engine exhaust nozzles for the 3 remaining X-51As. Regrettably, the following 2 X-51A flights concluded prematurely. During the second X-51A flight, the vehicle was propelled by the rocket to slightly above Mach 5 before disengaging and activating the scramjet engine fueled by ethylene. However, upon attempting to transition to JP7 fuel operation, an inlet unstart occurred. Despite efforts to restart and optimize engine start conditions, the vehicle remained unsuccessful in its attempts. It maintained controlled flight orientation until ultimately descending into the ocean within the test range. In the case of the third X-51A, a successful separation from the B-52 was followed by 16 seconds under the rocket booster, after which a fault was detected with one of the cruiser's control fins. Subsequently, upon detachment from the rocket booster roughly 15 seconds later, the cruiser lost control due to the malfunctioning fin and was ultimately lost. Conversely, the final flight of the X-51A on May 1, 2013 proved to be the most successful, achieving all experiment objectives. The cruiser traversed more than 230 nautical miles in just over 6 minutes, attaining a peak speed of Mach 5.1. In totality, the X-51A program amassed over 9 minutes of invaluable data, marking a groundbreaking accomplishment and validating the feasibility of air-breathing, high-speed scramjet propulsion utilizing hydrocarbon fuel. On May 1, 1960, amidst the escalating tensions of the Cold War, Gary Powers found himself in a harrowing situation. His U-2 aircraft, employed for reconnaissance missions, was struck by Soviet surface-to-air missiles, plummeting from 70,000 feet to 30,000 feet before Powers managed to release himself and bail out from the damaged cockpit. Meanwhile, at Lockheed's Skunk Works in Burbank, California, a team of engineers had already embarked on a groundbreaking project, the development of an aircraft that would revolutionize intelligence gathering. This aircraft, envisioned to fly faster and at greater altitudes than any before it, with minimal radar cross-section, was deemed essential in the tense geopolitical climate of the time. President Eisenhower recognized the strategic importance of airborne reconnaissance, particularly in light of the U-2's contributions. In response to the urgent need for an aircraft resistant to enemy fire, Lockheed received a directive from its government client in Washington to create the seemingly impossible, a plane impervious to interception. Led by the renowned aircraft designer Kelly Johnson, the Skunk Works team was renowned for its ability to deliver groundbreaking technologies under tight deadlines. The U-2 project was a testament to their resourcefulness, creativity, and unwavering determination in the face of technological challenges. The task at hand was unprecedented. Johnson acknowledged that every aspect of the aircraft had to be innovated from scratch. Undeterred by the daunting nature of the endeavour, he committed Skunk Works to achieve the seemingly insurmountable goal of having the revolutionary aircraft operational within a mere 20 months. The envisioned aircraft was unlike anything seen before. It was designed to sustain speeds exceeding 2,000 miles per hour for extended durations, a feat unparalleled in aviation history. Conventional airframes would succumb to the extreme temperatures generated by friction with the atmosphere at such velocities, necessitating radical innovations in design and materials. The challenges posed by the extreme temperatures anticipated on the aircraft's leading edges, exceeding 1,000 degrees Fahrenheit, presented formidable hurdles in design and material selection. Titanium alloy emerged as the sole viable option for the airframe, offering the strength of stainless steel, lightweight properties, and resilience to the intense heat. However, working with titanium proved to be a complex endeavour. The brittle nature of the alloy demanded meticulous handling, leading to frustrations on the Skunk Works assembly line and necessitating specialized training for Lockheed's machinists. Conventional tools, plated with cadmium-plated steel, proved detrimental to titanium, prompting the development and fabrication of new tools crafted from titanium itself. While the leading edges of the aircraft faced scorching temperatures, the exterior environment outside the cockpit window could plummet to -60 degrees Fahrenheit. Addressing the challenge of heat dissipation across the entire airframe, Ben Rich of Skunk Works drew inspiration from a basic lesson learned in university. Black paint possesses both heat-emitting and heat-absorbing properties. Consequently, the aircraft was coated in black paint, earning it the moniker Blackbird. The inaugural iteration of the Blackbird, designated the A-12, embarked on its maiden flight on April 30, 1962. Subsequently, the single-seat A-12 evolved into the larger SR-71, featuring an additional seat for a reconnaissance systems officer and increased fuel capacity. The SR-71 conducted its maiden flight on December 22, 1964. Efforts to diminish the Blackbird's radar signature aimed to further minimize the likelihood of detection and interception. Despite promising initial test outcomes, concerns over Soviet radar advancements prompted the US government to demand an even smaller radar profile, underscoring the ongoing quest for technological superiority in the realm of aerial reconnaissance. Redesigning surfaces to minimize radar reflection, relocating engines to a more inconspicuous mid-wing position, and incorporating radar-absorbing elements into the paint were among the meticulous adjustments made to the Blackbird's design. Subsequently, a full-scale model of the aircraft underwent radar testing at a clandestine location in the Nevada desert, meticulously scheduled to evade detection by Soviet satellites. The outcomes were striking. The Blackbird model, spanning over 100 feet, appeared on Soviet radar as larger than a bird, yet smaller than a man, effectively reducing its radar cross-section by an impressive 90%. The urgency to deploy the Blackbird heightened on October 27, 1962, amidst the Cuban Missile Crisis, following the tragic death of Air Force Major Rudolph Anderson during a U-2 reconnaissance mission over Cuba, struck by a Soviet surface-to-air missile. Skunk Works redoubled its efforts, confronting and surmounting the myriad challenges encountered during flight testing as it pushed the boundaries of aeronautical achievement. Breaking records with nearly every flight, the Blackbird reached a sustained speed surpassing Mach 3 on July 20, 1963, soaring to an astonishing altitude of 78,000 feet. As the aircraft traversed the skies at 3,000 feet per second, conventional navigation norms became obsolete, replaced by landmarks such as mountain ranges, coastlines, and expansive bodies of water. Piloting the Blackbird demanded unwavering focus and skill, with pilots facing the formidable task of navigating at incredible speeds and altitudes. Despite the formidable challenges, the exhilarating responsibilities of flying the Blackbird left pilots awestruck and exhilarated. Air Force Colonel Jim Watkins reflected on the experience, describing it as almost transcendent, with memories of soaring at 85,000 feet and Mach 3 evoking profound emotions even years later. At such unparalleled speeds and altitudes, even the most advanced air defense systems stood little chance of intercepting the Blackbird. When enemy aircraft weapons were launched, a warning light illuminated on the control panel, signaling imminent danger. However, for the pilot, this often marked the extent of the threat, as surface-to-air missiles consistently veered off course, detonating miles away from their intended target. The Blackbird's legacy is adorned with numerous records. It holds the distinction of being the world's fastest and highest-flying manned aircraft. During its retirement journey from Los Angeles to Washington in 1990, en route to its final resting place in the Smithsonian Air and Space Collection, the aircraft traversed the entire continental United States in a mere 67 minutes. Above all, the Blackbird fulfilled its strategic imperatives, providing invaluable mission-critical reconnaissance for over 2 decades. The extent of its intelligence-gathering contributions during the Cold War remains largely known only to a select few. Nevertheless, its reputation as a transformative force will endure for generations to come, symbolizing innovation, resilience, and technological prowess in the annals of aviation history. The Bell X-2 was indeed a pioneering aircraft in the realm of high-speed and high-altitude research. Developed jointly by Bell Aircraft Corporation, the U.S. Air Force, and the National Advisory Committee for Aeronautics (NACA), the X-2 aimed to explore the challenges of supersonic flight and expand the boundaries of speed and altitude reached by previous research aircraft like the X-1 series. Testing of rocket-launched X-2 models began in 1946 at Wallops Island, Virginia, under the auspices of the NACA's Pilotless Aircraft Research Division, PARD. These tests focused on gathering stability and control data crucial for the X-2's development. Collaborative efforts between NACA and Bell engineers also led to the design of a pilot escape system for the X-2, a critical safety feature given the extreme conditions it would face. NACA's Langley Memorial Aeronautical Laboratory in Hampton, Virginia, played a significant role in evaluating various aspects of the X-2's design, utilizing facilities such as the spin tunnel and supersonic wind tunnels. Additionally, NACA was responsible for equipping the X-2 with scientific instrumentation vital for collecting data during flight tests. Constructed at Bell's plant in Wheatfield, New York, the X-2 airframes were built using sturdy materials like stainless steel and K-monoll, ensuring their resilience under the stresses of high-speed flight. Powered by a 2-chamber Curtiss-Wright XLR-25 throttleable liquid-fuel rocket engine, the X-2 boasted a variable thrust rating capable of propelling it to incredible speeds. Safety was a paramount concern in the X-2's design, exemplified by the inclusion of an escape capsule for the pilot. In the event of an emergency, the nose assembly will be jettisoned, deploying a stabilizing parachute to bring the capsule to a safe altitude. The pilot could then manually open the canopy and bail out, ensuring their survival in challenging circumstances. The operational procedures for launching and piloting the X-2 were carefully orchestrated to ensure safety and gather valuable data during flight tests. A modified Boeing B-58 bomber served as the carrier aircraft, lifting the X-2 to launch altitudes of approximately 30,000 feet. Once in position, the pilot would enter the X-2 and prepare for launch. During a planned powered flight, the pilot would release the X-2 from the bomber and ignite the rocket engines to propel the aircraft to high speeds and altitudes. Following engine burnout, the pilot would guide the X-2 in an unpowered descent, aiming for a landing on the surface of Rogers Dry Lake at Edwards Air Force Base, California. The first unpowered flight of X-2, serial number 46674, occurred on August 5, 1954, with Lieutenant Colonel Frank Pete Everest at the controls. Meanwhile, due to the decision to install the first available engine in airframe 46674, airframe 46675 was designated for glide tests. It arrived at Edwards on April 22, 1952, and after 2 captive flights, Bell test pilot Gene L. Skip Ziegler conducted the first glide flight on June 27th. However, a rough landing caused some damage, delaying the second glide flight until October 8th. 2 days later, Air Force test pilot Major Frank K. Pete Everest successfully completed the third glide flight of the X-2. The return of the X-2 to Bell's plant in New York marked a significant phase in its development, particularly with the installation of the engine in the second airframe, 46675. Captive flights with the newly installed engine were conducted over Lake Ontario, aiming to test various systems and components. Tragically, during one of these flights to check the liquid oxygen system, an explosion occurred, resulting in the loss of the X-2 and severe damage to the accompanying B-50 bomber. The accident claimed the lives of Skip Ziegler, the X-2 test pilot, and B-50 crew member Frank Wolkow. Despite the setback, the X-2 program persisted. The following day after the accident, preparations began for the X-2's journey to Edwards Air Force Base beneath the modified B-50D. Once at Edwards, technicians at the NACA High-Speed Flight Station commenced the installation of instrumentation to collect handling qualities data. Additionally, on the recommendation of the NACA, the Air Force acquired a Goodyear Electronic Digital Analyzer (GEDA) analog computer. NACA project engineer Richard E. Day programmed the GEDA to serve as a rudimentary flight simulator for the X-2, aiding in further evaluations and testing. Despite the setbacks and challenges, the X-2 program continued to push the boundaries of supersonic flight research. The first attempt at a powered flight occurred on October 25, 1955, but a nitrogen leak led to a change in the flight plan, with Everest completing the mission as a glide flight. Finally, on November 18, 1955, Everest successfully completed the first powered X-2 flight, igniting only the 5,000-pound thrust rocket chamber and achieving a maximum speed of Mach 0.95. Despite several aborted attempts, Everest completed a second powered flight on March 24, 1956, this time igniting the 10,000-pound thrust rocket chamber. The first supersonic X-2 flight occurred on April 25, 1956, with both rocket chambers ignited. The aircraft reached a speed of Mach 1.4 and climbed to a maximum altitude of 50,000 feet, marking a significant milestone in the X-2 program's quest to explore the realm of supersonic flight. The X-2 program continued to push the boundaries of high-speed flight, with Lieutenant Colonel Pete Everest achieving speeds up to Mach 2.53 in May 1956. On May 25th, Captain Ivan C. Kincello piloted the X-2 for the first time, successfully completing a supersonic flight despite having to shut down the engine prematurely due to a malfunction. In June, the aircraft underwent modifications, including the installation of engine nozzle extensions to enhance performance. Everest conducted a supersonic checkout flight of the modified X-2 on July 12th. His final flight in the X-2 on July 23, 1956, saw him achieve a speed of Mach 2.87 at an altitude of 68,000 feet, earning him the title of Fastest Man Alive. Following Everest's departure, Kincello assumed the role of X-2 project pilot, conducting high-altitude missions. On August 3, 1956, he successfully climbed to 87,750 feet while gathering stability data. On the same day, NACA Director Hugh L. Dryden requested the loan of the X-2 for research purposes. While the Air Force continued to fly the X-2 in pursuit of its maximum altitude capability, Kincello achieved a remarkable altitude of 126,200 feet on September 7, 1956, earning him the title of First of the Spacemen. This altitude record stood until the X-15 program. Despite several additional flight attempts, Kincello encountered aborts, concluding his remarkable achievements in the X-2. The tragic loss of Captain Milburn G. Mel Apt during his historic flight in the X-2 on September 27, 1956, marked a somber moment in the program's history. Apt's flight, which saw him become the first person to fly faster than 3 times the speed of sound, reaching a speed of 2,094 miles per hour, Mach 3.196, was a remarkable achievement in high-speed flight research. However, the elation of this milestone was overshadowed by the sudden turn of events as Apt initiated a sharp turn back towards Edwards, leading to a control divergence known as inertial coupling. The X-2 began tumbling uncontrollably, and despite Apt's efforts to jettison the escape capsule, he was unable to extract himself before the capsule struck the ground. Apt's untimely death served as a poignant reminder of the risks inherent in pushing the boundaries of aerospace research and exploration. His legacy, however, lives on as a testament to the courage and dedication of those who endeavor to advance our understanding of high-speed flight and aerospace technology. The F-15 Eagle indeed holds a special place in the history of American military aviation. Introduced in the 1970s, it has consistently proven itself as a formidable air superiority fighter, with an unmatched record of aerial victories and a reputation for performance excellence. Designed to excel in dogfights and to maintain air superiority, the F-15 has demonstrated exceptional speed, agility, and weapon-carrying capabilities. Its powerful engines, advanced avionics, and robust airframe make it a potent force in both air-to-air combat and air-to-ground missions. Over the years, the F-15 has undergone several upgrades and variants, ensuring its relevance and effectiveness in modern warfare scenarios. The F-15E Strike Eagle, for example, is a dual-role fighter capable of both air-to-air and air-to-ground missions, further enhancing the aircraft's versatility and combat capability. Despite the emergence of newer aircraft like the F-35 Lightning II, the F-15 Eagle remains an integral part of the US Air Force's fleet, providing unmatched air superiority capabilities and serving as a symbol of American military aviation prowess. Absolutely, the F-15 Eagle emerged during this intense period of geopolitical competition, and it was a direct response to the need for a superior air combat platform. As both the United States and the Soviet Union sought to outmatch each other in military technology, the development of high-performance fighter jets became paramount. In this context, the F-15 was conceived as a way to maintain air superiority in the face of evolving threats. Its design prioritized speed, maneuverability, and firepower, ensuring that it could effectively engage and defeat enemy aircraft in aerial combat scenarios. The F-15's legendary status stems from its exceptional performance characteristics. With its powerful engines, advanced avionics, and agile airframe, it could outmaneuver and outgun virtually any adversary it encountered. Its combination of speed and agility earned it the reputation of being able to turn on a dime, making it a formidable opponent in dogfights. Furthermore, the F-15's versatility allowed it to adapt to various mission requirements, ranging from air superiority and interception to ground attack and reconnaissance. This flexibility made it a valuable asset for the US military, capable of fulfilling a wide range of roles with precision and effectiveness. Overall, the F-15 Eagle's legacy as a legend of the skies is rooted in its unparalleled performance, adaptability, and reliability, which have ensured its continued relevance in modern military operations. Indeed, the development of new fighter jets during the Vietnam War was driven by the urgent need to counter the threat posed by adversary aircraft, particularly the Soviet-built MiG-21s and the emerging MiG-25 Foxbat. The agility and speed of these enemy fighters presented a significant challenge for American pilots, leading to a concerted effort to design and deploy more capable aircraft. McDonnell Douglas's success in securing the contract for the new fighter, which would eventually become the F-15 Eagle, marked a pivotal moment in military aviation history. The F-15 was specifically engineered to excel in air combat, with a focus on speed, maneuverability, and firepower. The fixed delta wings and vertical stabilizers of the F-15 were integral to its design, providing the necessary aerodynamic characteristics for high-speed flight and agile maneuvering. Combined with powerful twin engines, the F-15 boasted exceptional performance capabilities, allowing it to effectively engage and defeat enemy aircraft in aerial combat scenarios. The F-15's inaugural flights in 1972 marked the beginning of a new era in air superiority, with the aircraft quickly demonstrating its formidable capabilities during testing and evaluation. Its successful development and deployment paved the way for a new generation of fighter jets that would dominate the skies for decades to come. The evolution of the F-15 Eagle series, spanning several generations, underscores its enduring significance in modern military aviation. From its initial deployment in the mid-1970s, the F-15 has undergone continuous development and improvement to maintain its status as one of the world's premier fighter jets. The introduction of successive models, including the F-15AB, F-15CD, and the F-15E Strike Eagle, reflects a commitment to enhancing the aircraft's capabilities to meet evolving operational requirements. Despite these advancements, the fundamental design of the F-15's airframe has remained consistent, a testament to its enduring effectiveness and versatility. Key specifications highlight the F-15's formidable performance attributes. With a length of approximately 64 feet and a wingspan of 43 feet, the aircraft offers a spacious cockpit environment for its crew. Its unfueled weight of 31,700 pounds allows for agile maneuverability, while a maximum takeoff weight of 68,000 pounds accommodates extensive weapon payloads. The Pratt & Whitney F100 P220 turbofan engines powering the F-15 deliver impressive thrust capabilities, enabling the aircraft to achieve speeds of up to 1,875 miles per hour, or Mach 2.5. These engines also provide a range of up to 2,173 nautical miles and enable operations at altitudes of up to 65,000 feet, ensuring the F-15's versatility across a wide range of mission profiles. Overall, the F-15 Eagle's enduring legacy as a high-performance fighter jet underscores its continued relevance in contemporary military operations, reflecting a blend of proven design excellence and ongoing technological innovation. The F-15's impressive speed and agility, coupled with its advanced avionics and weapon systems, make it a formidable force in aerial combat. As the fastest fighter jet ever deployed by the American military, its ability to accelerate vertically immediately after takeoff sets it apart from its contemporaries. The F-15A's introduction of pioneering technologies such as the head-up display and advanced avionics laid the foundation for subsequent upgrades that have kept the aircraft at the forefront of aerial warfare. These enhancements have ensured that the F-15 remains capable and competitive against evolving threats. While its sleek design and impressive performance may capture attention, it's essential to remember that the F-15 is fundamentally a combat aircraft designed for military operations. Equipped with a range of weapons, including an internal 20mm multi-barrel gun for close-range engagements, the F-15 is prepared for various mission scenarios. The F-15E Strike Eagle, the latest iteration of the F-15 series, boasts a diverse arsenal of weapons, including guided air-to-air missiles deployed on its hardpoints. These advanced weapons systems provide the Strike Eagle with lethal precision and effectiveness in modern conflicts, where dogfights are rare and long-range engagements are more common. In summary, the F-15 Eagle's combination of speed, agility, advanced avionics, and potent weaponry makes it a versatile and formidable asset in the American military's arsenal, capable of meeting the challenges of contemporary warfare with unparalleled effectiveness. The F-15E Strike Eagle's versatility extends to its ability to carry a variety of air-to-surface weapons, including the GBU-15 glide bomb. Equipped with real-time guidance, the GBU-15 can be directed while in flight, allowing for precise targeting. Originally used by both the F-15E and the F-111F Nighthawk, the retirement of the F-111F has made the GBU-15 exclusive to the F-15 platform. While squadrons of F-15s were formed in the 1970s, they saw limited action for many years. However, the aircraft's combat prowess was showcased during the Gulf War, specifically Operation Desert Storm in Iraq. Remarkably, not a single F-15 was lost due to enemy action during this conflict, with all losses attributed to accidents. Since its introduction, F-15 pilots have confirmed 104 kills in air-to-air combat engagements. During Operation Desert Shield, which preceded Desert Storm, coalition forces achieved 44 air-to-air victories over Iraqi forces, with 40 of those victories attributed to various versions of the F-15. In a notable engagement during NATO operations over Kosovo in 1999, Captain Jeff "Claw" Hwang demonstrated the F-15's effectiveness by shooting down 2 MiG-29 Fulcrums with AIM-120 missiles while piloting an F-15C. For his actions, Captain Hwang was awarded the Distinguished Flying Cross, highlighting the aircraft's continued importance in modern aerial operations. The F-15's role in military operations continued into the 21st century with Operation Enduring Freedom, which commenced in 2001 with the invasion of Afghanistan and later extended to Iraq. F-15s played a crucial part in these operations, with some aircraft conducting daily missions equipped with Handle 5,000-pound bunker buster bombs or AGM-130 guided missiles. In a remarkable incident during Israeli training exercises in 1983, an F-15 was involved in a mid-air collision that resulted in one of its wings being torn off. Despite the severe damage, the pilots, unaware of the extent of the loss, managed to land the aircraft safely with just one wing remaining. While many military aircraft designed decades ago have become obsolete, the F-15 remains relevant and continues to be manufactured. Boeing has taken over production after merging with McDonnell Douglas. The F-15E Strike Eagle represents the most advanced version, equipped with cutting-edge avionics and enhanced targeting systems. While the USAF intends to keep some of its newer F-15E aircraft in service, it's also looking towards the future with the development of the F-15EX Eagle II. This newer version will come equipped with various enhancements, including the Open Mission System (OMS), allowing for easy upgrades with future updates, and helmet-mounted situational awareness displays. The acquisition process for the F-15EX is already underway, although delivery of the first batch has been delayed. Nevertheless, these aircraft are expected to enter service sometime in 2024, ensuring the USAF remains equipped with advanced and capable fighter jets for its missions. The longevity of the F-15 is indeed remarkable, especially in an era where technological advancements often lead to the retirement of older aircraft. While some iconic planes, like the F-14 Tomcat, have been phased out, the F-15 has continued to evolve with upgrades and improvements, ensuring its relevance on the modern battlefield. The upcoming F-15EX Eagle II represents the latest iteration of this enduring aircraft, incorporating cutting-edge technology and enhancements across its systems. With features such as fly-by-wire flight controls, electronic warfare capabilities, and powerful engines, the F-15EX will offer enhanced performance and capabilities compared to its predecessors. Furthermore, its advanced radar system will enable pilots to track multiple targets simultaneously with precision, further enhancing its effectiveness in combat scenarios. Overall, The F-15's adaptability and continuous upgrades ensure that it will remain a vital asset to military readiness for years to come. Absolutely, the inclusion of advanced systems like the Joint Helmet-Mounted Cueing System 2 further enhances the pilot's situational awareness and combat effectiveness. Additionally, the development of the Silent Eagle variant, incorporating stealth technologies, demonstrates the adaptability of the F-15 platform to incorporate modern features while retaining its core capabilities. Indeed, in a landscape dominated by stealth fighters, the F-15's cost-effectiveness and versatility make it a valuable asset for scenarios where stealth may not be the decisive factor. Its lower operational and acquisition costs make it an attractive option for missions where other factors such as payload capacity and range are prioritized over stealth. As a result, the F-15 continues to serve as a formidable fourth-generation fighter, ensuring that its legacy endures and that it remains a vital component of military air power for the foreseeable future. The spy satellite images depicting the massive Soviet aircraft sparked alarm within the Pentagon. The dimensions of the aircraft, with engine intakes resembling small cars and wings of considerable size, suggested capabilities surpassing those of America's leading aircraft, such as the McDonnell F-4 Phantom II. These prototypes mark the early stages of what would later become known as the Mikoyan-Gurevich MiG-25 Foxbat. Following its public debut in July 1967, including speeds up to 1,852 miles per hour and altitudes exceeding 123,520 feet, the MiG-25 appeared to present a formidable challenge to Western superiority, particularly against the Mach 3.2 Lockheed SR-71 Blackbird spyplane. However, the perception of the MiG-25 as a technological marvel eventually proved deceptive. In reality, it fell short of the hype surrounding it, akin to a Potemkin village. The surveillance failure, reminiscent of the missile gap exploited by John F. Kennedy during his presidential campaign in 1960, also contributed to the exaggerated fear of the Foxbat's capabilities. Nevertheless, the MiG-25 served its purpose as an interceptor, effectively deterring the SR-71 from entering Soviet airspace for several years. This uncertainty surrounding the true potential of the MiG-25 persisted in Western military circles for some time, emphasizing its significant impact despite its eventual shortcomings. The MiG-25 Foxbat commanded attention not only for its purported capabilities, but also for its sheer size, comparable to World War II heavy bombers. Towering over technicians and ground crews in photographs, it conveyed an imposing presence despite its rudimentary appearance. However, the Soviet approach to constructing the Foxbat differed significantly from Western counterparts due to limitations in titanium technology. While titanium was essential for high-speed flight due to its resistance to the heat generated by skin friction at supersonic speeds, the Soviets lacked the expertise and tools to work with this material effectively. Instead, they resorted to stainless steel, despite its weight disadvantages compared to aluminum. As a result, the MiG-25's fuselage consisted of a single welded steel fuel tank aft of the cockpit. The use of steel presented challenges in craftsmanship, with some observers mistaking factory-fresh skinning for crude repair patches. Despite its unconventional construction, the Foxbat was designed to fulfill its strategic role, targeting high-altitude Western bombers like the Convair B-58 Hustler and the North American B-70 Valkyrie. The Soviet Union's reliance on ground control for virtually all aspects of the Foxbat's operation reflected their centralized command structure. Pilots were tasked with executing predetermined missions under strict guidance, highlighting the USSR's preference for centralized control over individual initiative. The US strategic response to the introduction of the MiG-25 Foxbat and advancements in Soviet air defenses led to a significant shift in tactics. The emergence of more advanced surface-to-air missiles, SAMs, made high-altitude penetration missions into Soviet airspace increasingly perilous for bombers. In response, Strategic Air Command (SAC) revised its tactics, emphasizing low altitude, high speed, and stealthy approaches to evade enemy defenses. This shift in strategy led to the retirement of the Convair B-58 Hustler and the cancellation of the North American B-70 Valkyrie, both of which were designed for high-altitude, high-speed operations. The new approach required aircraft to fly low to the ground, reducing their radar cross-section and minimizing exposure to enemy radar and SAMs. The MiG-25's performance was largely dictated by its engines, particularly the Tumansky R-15. While the engine design lacked sophistication, its unique 3-ring afterburner fuel nozzles allowed for efficient operation in sustained supersonic flight. At high speeds, the engine functioned akin to a ramjet, with much of the intake air bypassing the low-pressure compressor and feeding directly into the afterburner. However, sustaining high speeds imposed significant challenges on jet engines, particularly regarding air intake. At speeds exceeding Mach 2, the engine intake faces immense pressure, necessitating careful design to regulate airflow and prevent engine damage. Lockheed's solution for regulating air intake on the SR-71 involved movable cones within each engine's intake, which adjusted their position based on the aircraft's speed. As the SR-71 accelerated, these cones moved inward to restrict excessive airflow into the engine. In contrast, the MiG-25 attempted a similar approach, with movable ramps in its intakes, but they proved ineffective at the aircraft's highest speeds. The tremendous airflow demanded significant fuel flow, causing the engines to overheat and malfunction. Despite the limitations of the engines, the MiG-25 showcased the best of Soviet metallurgical capabilities at the time. However, the engines were not capable of sustaining speeds beyond Mach 2.83, which was considered the aircraft's operational top speed. Attempts to push the aircraft to its theoretical top speed of Mach 3.2 resulted in catastrophic engine failures, with the cause being literally sucked out of the tailpipe. Nevertheless, the MiG-25 inadvertently influenced the development of American fighter aircraft. Concerns over the capabilities of the MiG-25 prompted the US Air Force to accelerate the development of a new air superiority fighter, initially designated the FX. This competition led to the creation of the F-15 Eagle, designed by McDonnell Douglas. The F-15, intended to surpass the capabilities of the MiG-25, became one of the most successful air superiority fighters in history, boasting an impressive record of 104 shootdowns without a single loss in air-to-air combat. The MiG-25, despite its flaws, had a unique feature that endeared it to the Russian personnel who maintained it: its unconventional air conditioning system. This system relied on the evaporation of a mixture of distilled water and nearly 240 litres of near-pure grain alcohol. After missions, MiG-25s would often return with some of this concoction still in its tank, but the airborne vodka quickly found its way into the canteens of mechanics. The convenience of refilling the system from small bowsers with spigots further contributed to its popularity among maintenance crews. It's no wonder the MiG-25 earned the nickname Flying Restaurant due to this unusual feature. The MiG-31, known as the Foxhound by NATO, was developed by the Soviet Union in response to the perceived threat posed by NATO low-level strike aircraft and cruise missiles. It was designed as a successor to the MiG-25 Foxbat high-altitude interceptor and aimed to address some of the shortcomings of its predecessor. One of the key advantages of the MiG-31 was its ability to operate at low altitudes, a capability lacking in the MiG-25. Additionally, the MiG-31 featured more efficient engines that allowed for greater combat range at supersonic speeds, addressing a limitation of the MiG-25. The new aircraft also aimed to mitigate the issue of engine failure at high speeds experienced by the MiG-25. The development of the MiG-31 began with the YE-155MP prototype, which conducted its maiden flight in 1975. Production of the final model commenced in 1979, and by 1982 it had been incorporated into the Soviet military's anti-air defense regiment. As advancements were made, the Soviets pursued the development of the MiG-31M, an upgraded variant capable of launching long-range R-37 missiles with a range of up to 200 kilometers, as well as R-77 medium-range air-to-air missiles. These enhancements further solidified the MiG-31's role as a crucial component of the Soviet Air Force's arsenal. The MiG-31 continues to serve as a vital asset in the Russian Air Force, frequently deployed in various operations, including recent events such as the invasion of Ukraine. Its longevity is a testament to its enduring relevance and effectiveness, with plans for its retirement extending well into the 2040s. The evolution of the MiG-31 saw several iterations aimed at enhancing its capabilities, although some projects were hindered by budget constraints and geopolitical changes. The MiG-31M, equipped with the Zaslon M radar, upgraded avionics, and more powerful engines, represented a significant advancement. However, production of this model was halted due to financial limitations towards the end of the Soviet Union. Subsequent variants, such as the MiG-31B, continued to improve upon the platform's capabilities, featuring enhancements like improved radar systems, digital processors, and advanced air-to-air missiles like the R-33S. Existing aircraft upgraded to this standard were designated MiG-31BS. The development of specialized versions, such as the MiG-31D anti-satellite variant, showcased the aircraft's versatility in adapting to different mission requirements. The introduction of the MiG-31BM in 1998 marked a significant milestone in the development of the aircraft, addressing previous shortcomings while introducing new capabilities. Building upon earlier concepts like the MiG-31F, which focused on multi-role capabilities, the MiG-31BM emerged as a versatile platform capable of ground attack missions, long-range interceptions, precision strikes, and defense suppression tasks. One of the key advancements of the MiG-31BM was its ground attack capabilities, a departure from its previous role primarily as an interceptor. Equipped with advanced cockpit displays and the Zaslon AM radar with enhanced range, operators could effectively deploy precision-guided missiles, expanding the aircraft's operational versatility. Furthermore, the MiG-31BM's ability to function as an early warning aircraft and airborne command unit added strategic value to its role in coordinating aerial operations. By leveraging its radar capabilities and data link systems, the MiG-31BM could provide crucial radar information to multiple sources and coordinate the movements of other aircraft with less advanced radar technology. The upgrade to the MiG-31BM standard also extended the operational life of the aircraft by an additional 15 years, ensuring its continued relevance in modern air defense strategies. As of 2017, a significant portion of Russia's interceptor fleet had been updated to the MiG-31B and MiG-31BMS configurations, reflecting the aircraft's enduring importance in the country's air defense capabilities. The announcement of a further life extension program for the MiG-31 Foxhounds in July 2020 underscores Russia's commitment to modernizing its air defense capabilities and ensuring the continued relevance of this formidable interceptor aircraft. In addition to its traditional role as an interceptor, a modern variant known as the MiG-31K has been developed, specifically modified to carry Kh-47M2 Kinzhal air-launched hypersonic cruise missiles. With a remarkable speed of Mach 10 and a range of 2,000 kilometers, these missiles provide the MiG-31K with enhanced strike capabilities, further enhancing its versatility in contemporary warfare scenarios. The MiG-31 Foxhound boasts impressive dimensions, with a length of 22.69 meters and a height of 6.15 meters and a maximum takeoff weight of 46,000 kilograms, making it the heaviest combat jet ever constructed for air-to-air combat. Its aerodynamic design, characterized by a streamlined body and delta wings, enables it to achieve high speeds, particularly at low altitudes. Constructed primarily from nickel steel, titanium, aluminum alloy, and composite materials, the MiG-31's airframe is designed to withstand the rigors of high-speed flight and combat operations. The delta wings feature square tips and a negative slant, enhancing lift and maneuverability compared to its predecessor, the MiG-25. Equipped with 4 underwing pylons and fuel tanks capable of holding a total volume of 5,000 litres, the MiG-31 has ample capacity for carrying external stores and fuel for extended missions. Its Solovyev D-30 F6 turbofan engines, each providing a takeoff thrust of 15,500 kilograms, enable it to achieve a top speed of approximately Mach 3, ensuring rapid response and interception capabilities. With impressive climb and range capabilities, including a climb rate of 208 meters per second, a ferry range of 3,300 kilometers, and a combat range of 720 kilometers, the MiG-31 remains a formidable asset in Russia's air defense arsenal, capable of effectively countering airborne threats in various operational scenarios. The MiG-31 Foxhound indeed represents a pinnacle of technological innovation, featuring a sophisticated cockpit equipped with state-of-the-art digital avionics systems. The cockpit incorporates liquid crystal displays, LCDs, that provide pilots with clear instrument readings and radar information, ensuring optimal situational awareness during flight operations. At the heart of the MiG-31's avionics suite is the formidable N007 Zaslon radar, renowned for its exceptional capabilities. In its latest iteration, this radar system can scan up to 200 kilometers in all directions, effectively providing comprehensive coverage of the airspace. It boasts the ability to simultaneously track up to 10 targets and engage up to 4 of them concurrently if they fall within its operational range. Operated by the weapons system officer seated in the rear cockpit, the Zaslon radar is not only capable of detecting airborne threats, but also of receiving signals from early warning radar systems and airborne command and control platforms. Utilizing electronic beam steering technology, the radar antenna can be swiftly and precisely directed to maximize coverage and enhance target acquisition capabilities. Moreover, the MiG-31 features advanced sensor systems that further augment its situational awareness and threat detection capabilities. The Track While Scan (TWS) radar enables the aircraft to detect and track multiple radar-emitting targets simultaneously, whether airborne or ground-based. Additionally, the Infrared Search and Track (IRST) system enables the MiG-31 to passively detect and track heat signatures emitted by enemy aircraft and helicopters, enhancing its ability to engage targets effectively. With its integrated suite of advanced avionics and sensor systems, the MiG-31 Foxhound stands as a formidable interceptor aircraft, capable of maintaining air superiority and countering a wide range of airborne threats in modern combat scenarios. The MiG-31 Foxhound indeed possesses a formidable arsenal of weapons and advanced systems, making it a highly lethal platform in combat situations. In addition to its advanced radar and sensor suite, the aircraft is equipped with a Radar Warning Receiver (RWR) system, which provides real-time alerts to the operator regarding incoming threats. This capability allows the crew to react promptly to potential threats, enhancing the aircraft's survivability in hostile environments. Furthermore, the MiG-31's digital interference communication system enables seamless communication and data sharing among groups of aircraft, facilitating coordinated operations and enhancing situational awareness on the battlefield. This capability enables MiG-31s to exchange tactical information in real time and collaborate effectively with other friendly forces. Regarding its armament, the MiG-31 carries a diverse array of air-to-air missiles tailored for various engagement scenarios. The long-range Vinepol R-33 missiles provide the aircraft with the capability to engage high-speed and distant targets effectively. The MiG-31 can also be armed with the AA-12 Adder missile and various Russian-made air-to-air ground missiles, including the AS Krypton anti-radiation missile, providing the aircraft with multi-role capabilities. To complement its missile armament, the MiG-31 is equipped with a potent built-in cannon, the GSH-623 gun, capable of delivering a high volume of fire. Overall, the MiG-31 Foxhound's combination of advanced avionics, robust weapons systems, and formidable firepower make it a formidable adversary in aerial combat and a key asset in Russia's air defense arsenal. The MiG-31 has indeed been a significant asset in Russia's air defense capabilities, with a substantial number still in service, both in Russia and in Kazakhstan. However, its commercial success has been limited, with few export orders and cancellations of potential deals, such as the contract with Syria in 2007. Despite its commercial challenges, the MiG-31 has played a role in various conflicts, including the Russo-Ukrainian War, where it has been utilized for combat missions. Despite its commercial challenges, the MiG-31 has played a role in various conflicts, including the Russo-Ukrainian War, where it has been utilized for combat missions. Its participation in such conflicts underscores its continued relevance and effectiveness in modern warfare scenarios. Looking ahead, Russia's plans for the MiG-41, set to be a successor to the MiG-31, indicate the country's commitment to advancing its air defense capabilities. With anticipated improvements in speed and weaponry, including directed energy weapons, the MiG-41 aims to maintain Russia's edge in aerial combat for the foreseeable future.
A plane designed to fly faster and higher than any of its rivals. The Boeing 2707. This is the story of Kennedy's dream. In the summer of 1963, President John F. Kennedy announces a major new aerospace program.
I'm announcing today that the United States will commit itself to an important new program in civilian aviation.
He calls for America to build and fly a supersonic airline that will cruise at over 3,000 kilometers per hour. One of John Kennedy's heroes was John Glenn. Glenn was also the first man to fly America coast to coast at supersonic speed in the year 1957. Ever since that flight, Kennedy had dreamed of building an American supersonic transport. Others had that same dream.
The British began their supersonic aircraft program in 1943, midway through the war. It was a design, obviously, at that stage, which called for an aircraft to be capable of Mach 1.5. That's 1.5 times the speed of sound, or about 1,000 miles an hour.
The British had several projects. Among these were the Miles M-52 and the de Havilland DH-108 Smaller. But Britain was beaten to the prize by Chuck Yeager, flying the American Bell X-1.
To tell you the truth, I was hopping mad, because I realized we could have done it and we'd missed the boat by a cancellation. Not with the DH-108, but with the Miles M-52. I was to be the pilot of the Miles M-52, so I'd followed this carefully, and we were 80% ready for the first flight, when, without any warning, without any consultation, the aircraft was cancelled.
On October the 14th, 1947, the rocket-powered Bell X-1 became the first aircraft to fly faster than sound.
The British were really upset that the Americans had been first through the sound barrier, because British technology was ahead of the Americans. The British just fluffed it, lacked the guts to do it.
The reason the British gave for cancelling the Miles 52 was lack of knowledge surrounding what happens to an aircraft as it approaches the sound barrier.
When an aircraft approaches the speed of sound, several things happen. The most disturbing of which for the occupants of the aircraft is the aircraft begins to shake and rumble, depending on how rapidly or how slowly you approach the speed of sound. But in aerodynamic terms, a wave builds up, an area of compressibility builds up, a shock wave. And what that does is that causes increased drag and increased heating on the aircraft, such that as you approach the speed of sound, as the shock wave passes over the flying surfaces, what that does, it causes the wings to lose lift both above and below the wing. And that has a downward effect on the aircraft. So the aircraft will start to dive if you don't do anything else about it. You'll first start to notice the problem of approaching the transonic area, approaching the speed of sound from about 0.9, so 9/10 of the speed of sound at sea level. And there you'll begin to experience a buffet as the shockwave begins to build up. And as you approach the speed of sound, the closer you get to the speed of sound, the greater that buffet will be, until that moment when you pop through the other side and that shockwave is then traveling behind the aircraft. You then punch through into an area of far more stable air, an area of almost quietness, if you like.
By the mid-1950s, military aircraft were routinely flying beyond the sound barrier. But they did so only for short periods. Sustained supersonic flight was a much bigger problem than just punching a hole in the sound barrier.
Supersonic flight for passengers is actually very different from supersonic flight in the military context. If you're going to fly passengers at supersonic speed, you have to fly them for a long, long time at high speed, whereas military operations tend to be a quick dash.
Only one country decided to tackle the challenge. Defeated in the race through the sound barrier, the British now embarked on the design and development of a supersonic airliner. It was to signal the start of a race that would transform the world of aviation. On March the 10th, 1956, the British re-entered the supersonic stakes with a vengeance when the experimental Fairy Delta II captured the world absolute speed record at 1,820 kilometers per hour. The Fairy Delta II introduced a series of revolutionary features. A long, narrow delta, perfect for cruising beyond the sound barrier, and a drooping nose to allow the pilot a better view on takeoff and landing. Inspired by the success of the Fairy Delta, the British established a committee to coordinate the development of a supersonic airliner.
The most interesting aspect of the Fairy Delta II that we see on today's Concorde was the drooping nose. Now, what that is it is simply, as you see on Concorde, a nose that kinks. One of the problems with the delta-winged aircraft, and an aircraft that is designed for going supersonic speeds, is that in order to fly very fast, obviously you need something that is as aerodynamic as possible. The problem is they are very, very difficult to fly at low speeds. So when they come into land, they have a very high angle of attack, and very, very difficult then for the pilots to see what they're doing. So they then put this kink in the nose, if you like, to have this cantilevered nose, such that in takeoff and landing, to give the pilots better visibility, they put this design feature in, which we see today.
In March 1959, the preliminary design work had progressed to a point where the Supersonic Transport Committee was able to report its broad recommendations.
There were two main recommendations. The first was for a small, fairly simple aircraft to carry around 100 passengers and do about Mach 1.2. The second design was for a 150-seater that should have been capable of Mach 1.8, which was considerably bigger and considerably faster.
By 1959, the British thinking had crystallized into two projects. A medium-range supersonic airliner, which had a rather crazy M-shaped wing, very difficult to build. And the other project was the classic, what's now the classic long, thin delta for a supersonic airliner that could fly across the Atlantic.
Now would emerge a decision that would shape the whole future of the race to build a supersonic airliner.
The design study contract in 1960, the British made it a condition to BAC, who got the contract, that they should seek international collaboration for the building of the supersonic transporter.
The first country BAC approached was the United States. But in 1960, there was little interest shown in the USA for collaboration. So the British turned to France as a potential ally.
Eventually decided to cooperate because the supersonic airliner project was just too big for either of them to do on their own. It was helped by the fact that the two different design teams in France and in England had more or less come to the same conclusion about what the aircraft should look like.
The aircraft was to be a delta-winged design. It was to be called Concorde, a word common to both languages, which means agreement or harmony. But to become credible, Concorde needed customers in the airlines. In June 1963, Concorde received the major airline order that meant it would fly. And the order came not from Europe, but from America's own leading airline, Pan Am.
Such a good customer that they could go in and play one aircraft factory leader against another. And Chip didn't mind going in threatening and saying, look, if you don't do this, I'm going to get somebody else to do it. And if I have to go to Europe, I'm going to Europe. Tripp was an overpowering figure in the industry at that time.
Pan American Airways began operations on October the 28th, 1927, with the first scheduled international flight by a United States airline. A Fokker tri-motor airplane loaded with mail flew from Key West, Florida, and landed 1 hour and 10 minutes later in Havana, Cuba, a distance of 135 kilometers. Pan Am's 28-year-old founder was the legendary Wham Terry Tripp. It was Tripp's original bright idea that planes carrying mail can just as easily transport people. Putting seats in the back of each plane, he charged $100 to fly to Havana. Tripp was determined that Pan Am would always be the #1 U.S. airline.
In the post-war world, in the 1960s, Pan American Airlines was one of the big names. Most American airlines tended to fly inside America, but Pan Am had built his reputation on flying all around the world. And they did that by always buying the latest and best aircraft.
On October the 26th, 1958, Pan Am became the first U.S. airline to operate a jet passenger plane, a Boeing 707 christened Clipper America. It flew from New York to Paris, halving the normal flight time. Juan Tripp was also determined Pan Am would be the first airline to go supersonic.
If you joined Pan Am as a pilot in the late 1950s or 1960s, the first thing they told you was, you hang in there, guys, because you are going to fly supersonic. Pan Am saw that being the first to be with the supersonic airliner as you know, the thing that would brand the company as the place to go.
But the Pan Am decision was to trigger an American response. Within days of the announcement, on June the 5th, 1963, President John F. Kennedy proclaimed his government's intention to support the American aircraft industry in developing and building a supersonic transport that American airlines like Pan Am could fly.
When Kennedy heard that Pan American were going to buy the European Concorde, he was apoplectic. He was furious. And he phones up head of Pan Am, Juan Tripp, and just gives him a bawling out. And Tripp says, well, you know, the alternative is you give me an American supersonic airliner. So from that moment on, Kennedy decides he is going to get a hold of the American aircraft companies and he's going to make them build a supersonic airliner faster and higher in performance than the European rival.
And so the race began.
The immediate result of Kennedy's intervention in the race to build a supersonic transporter was the appropriation of $100 million worth of funding from Congress, which in 1963 was a serious amount of money.
Concorde now had an American rival. The question then became, who was going to build it? One obvious candidate was Douglas, the major builder of civil airliners, from the fabled DC-3 to the jet DC-8. But Douglas was too strapped for cash to compete. Other candidates were North American, who were already working on a big supersonic bomber, the B-50 Valkyrie, and Lockheed, which had major experience of supersonic craft such as the secret SR-71 Blackbird. There was also Boeing, the manufacturer of the mighty B-52 bomber and the well-established 707 airliner series.
Of all the American aircraft companies, paradoxically, Boeing was the one that had the most trouble in getting into the supersonic airline business. Boeing hadn't actually delivered a supersonic aircraft to anybody.
Its founder was William Boeing, the son of a wealthy lumberman. In 1903, Boeing dropped out of Yale University and headed for Washington State to make his fortune in the timber industry. In 1910, William Boeing went to Los Angeles for the first American Air Meet. He tried to get a ride in one of the airplanes, but not one of the dozen pilots participating in the event would oblige. Boeing came back to Seattle, determined to build and fly his own planes.
Bill Boeing was, some people think he was an inventor, but Bill Boeing was an innovator of the highest order. I think he has very few patents, perhaps if any, but he would look at a product and he could see where he could make it better.
On July the 15th, 1960, Boeing incorporated his airplane manufacturing business in Seattle, in an old boatyard. He hired boat builders whose skills in carpentry were ideal for the new aviation industry. The early Boeing company prospered, building seaplanes for the US Navy, then pursuit planes for the Army. But it was World War II that brought Boeing to the peak of success.
The war was starting in Europe, and Wright Field put out an order for bids. At this time, most of the airplanes were two-engine. We were still two-engine. Douglas was doing a two-engine bomber, and another company was doing a two-engine bomber. And Boeing went in to Wright Field and said, would this procurement cover a four-engine bomber? And everybody just went berserk because nobody ever conceived of a four-engine bomber.
This was the XB-15, a four-engine aircraft with a wingspan of 45 meters.
It was so big, you could tunnel out through the wing, and you could come into the nacelle, and you could make repairs in flight.
A smaller version of this giant would become famous, the B-17 Flying Fortress, that would fill the skies during World War II.
I think they ordered 13 or 14 what they call test airplanes, and that led to the Flying Fortress. I don't remember exactly how many were built, but it was around 13,000. And that airplane then went through the A series, B series, C series, all the way to H, as I recall. I'd say the story of the B-17 was it was such a versatile airplane, was able to keep carrying more bombs, more turrets.
As American men went to war, women built airplanes. Thousands of women took up the slack in the workforce and helped boost production at Boeing from 60 planes per month in 1942 to an astounding 362 planes per month by March 1944. The B-17 was followed in 1942 by the B-29 Superfortress. In Wichita, farm hands, housewives, and shopkeepers built B-29s on 10-hour shifts, day and night, during what later became known as the Battle of Kansas.
World War II transformed the fortunes of the Boeing company. Before that, it was a serious manufacturer, but planes were built in small numbers. World War II meant Boeing was producing vast numbers of giant bombers on huge assembly lines.
After World War II came the B-47, America's first jet bomber. And on April 15, 1952, Boeing test pilot Tex Johnston made the first flight with the B-52, which was to dominate the skies for the next 50 years. Then, Boeing took a gamble.
In the 1950s, Boeing was doing quite well in military contracts for the B-47 and the B-52 bombers. But no aircraft company, can afford not to look ahead because it takes a long while to develop aircraft. And so they took a bold decision. They decided, well, let's take some of the profits from the bombers, some of that technology, and see if we could mix that into an aircraft that passengers would want to use, that the airlines would want to buy.
We had all the knowledge of the B-47, the B-52, so it wasn't too big a job in the wind tunnel to develop a low-wing airplane that could be used as a tanker. And we knew they needed a tanker, so there had to be a tanker. And we hoped it could be a passenger airplane, although we weren't really sure that that was the case. So that's why the Dash 80 was born.
The Dash 80 took to the air under the control of Tex Johnston, who had flown the B-52. Johnston was determined to show Boeing had built a great plane. So he barrel-rolled the Dash 80 over the Seafair hydroplane course on Lake Washington on August 2, 1955, a maneuver that only nimble fighter aircraft usually do. Boeing's president, William Allen, was there to witness it.
And Allen turned completely white, looked over at his technical advisor, Wellwood Beale, and he said, "Did we authorize that?" And then just before he could turn around, here he came back again and did it once more.
Boeing's gamble paid off. The Dash 80 became the prototype for the KC-135, the first jet aerial tanker. And that turned into the Model 707, the first in a long line of Boeing commercial jet airliners. Boeing had done something clever with the 707, using about 1/10 of the fuel. Could carry as many transatlantic passengers a year as the $30 million Queen Mary ocean liner. Boeing had created a market and killed the passenger liner. In 1958, with the 707 entering service with Pan Am, Boeing set up a small group to concentrate on developing a supersonic passenger aircraft. By 1960, the company was spending over $1 million annually on the project. The design was designated the Boeing Model 733.
Boeing actually started work on supersonic passenger airliners very early on, right at the beginning of the 1950s. But in a kind of research way, is this possible? Where are the engines going? Where is the metallurgy going? But what you begin to see is by the end of the 1950s, they're starting to get quite serious about it. They're beginning to think this can be done.
With Kennedy's call for America to actually build the SST, the Model 733 could become reality at last. Throughout late 1963, the three contenders for the prize of building the American SST, Boeing, Lockheed, and North American, worked in secret on their designs. Could the late American competitor still capture the market? In late 1963, metal for the first Concorde was already being cut. Would America catch up? There was a recent precedent. The British Comet had been the first jet airliner in service in the 1950s. But a series of fatal crashes revealed serious design flaws that had resulted from the Comet being rushed into airline operation to beat the Americans. As a result, the Boeing 707 came from nowhere to dominate the skies of the 1950s and 1960s.
The Americans came late to the supersonic race. They wanted to leapfrog the Europeans, and so they decided to go faster. The Europeans were going for Mach 2.2, which meant they could build Concorde out of existing materials using existing technology. The Americans decided to go way up to Mach 3 through the so-called heat barrier, which meant that because of the stresses on the plane at those speeds and the heat that would build up on the fuselage, they had to use new materials. So the Americans were going for a technological breakthrough to try and get ahead of the Europeans and bury the competition.
To beat the competition, both at home and in Europe, Boeing proposed a plane that was far bigger than Concorde. It was designated the 2707.
Boeing realised that if they were going to beat the Anglo-French Concorde, they would have to be bigger, better and faster. So their design was for a faster aircraft and for one that would carry 2.5 times the number of passengers as Concorde. So instead of 120, we're looking at 277 passengers on board.
To help design its new 2707, Boeing built an amazing life-size mock-up. The aircraft was 93 meters long, a third bigger than Concorde. There were 277 seats, 30 first class and 247 tourist. 2.5 times the number of passengers the small Concorde was designed to carry. The seating layout in the 2707 was revolutionary. Till then, seating in planes was 2 cramped seats on either side of a single aisle, which made planes seem very claustrophobic.
Boeing decided that in order to entice people into this new aircraft with these fancy speeds, they'd have to offer a bit of something else. And so they made the fuselage bigger so they could get more seating in. Today we are very used to three sets of seats, 2 aisles. But this was the first time when Boeing was developing the supersonic airliner that they decided to introduce that into an aircraft.
By comparison, the Concorde has a very narrow fuselage and the old-fashioned till-abreast single-aisle layout. The 2707 would be powered by 4 massive turbojets, each capable of generating nearly 3 tons of thrust. At takeoff, the 2707 would weigh over 300 tons.
The Boeing 2707 had 2 other very interesting features. The first was a drooping nose, not unlike we see on Concorde today, to allow the pilots much better visibility in takeoff and landing, and then to be flicked up for that needle-like high-speed flight. The second design feature was also to do with the differences between low speeds for approach and landing and high speeds in supersonic, and that was the swing wing. The wing was able to pivot for those slow speed areas, making it easier and safer to fly when taking off and landing. But then when it was up above the Atlantic or Pacific or wherever it was going to go and approaching its speeds of Mach 2, you could sweep the wings back and get a very similar effect to the Delta.
The wings on the mock-up of the Boeing 2707 could be moved manually from fully aft with a 72-degree sweep to fully extended with a 30-degree sweep.
The Boeing supersonic airliner was really pushing the boundaries of aviation technology. They were going to go faster, they were going to go faster for longer, which meant new materials, new kinds of engines, new kinds of avionics. It was a risk.
One group who sought that were the Lockheed company, who were busy with their rival SST, the Lockheed L2000.
The Lockheed design for a supersonic airliner was simple, elegant, beautiful. No complex moving parts like a swing wing. They'd adopted the narrow delta that everyone knew was going to work. It was within the boundaries of what was possible. They were minimizing the risks, and that's why it was a serious competitor.
As the time for submitting final design entries drew closer, Boeing was still plotting to outdo the competition.
As the design process went on, it became obvious that the Boeing entry was going to be terribly complex, terribly expensive. That made the airlines who were going to have to buy and use the thing frightened. So Boeing started adding on more and more passengers in the hope that it could make a profit that would make up for the escalating costs of the aircraft in the first place.
Size does help you a little bit on efficiency, at least it has on the other airplanes, and so obviously you can go overboard and be too fast, but too big. But I think that we felt the Concorde was too small to be a successful system.
It was the last day of 1966 when the final design winner was announced. It was the revolutionary Boeing design.
I think it was a very tough competition. The reason we won the configuration was not necessarily that the airlines liked our configuration any better. My personal opinion is that I think that they felt that they would rather have Boeing build their commercial airplane than the other two manufacturers, because we were in the process of building commercial airplanes at that time and been working with the airlines. And my personal opinion is that we were picked as a company, not as a design.
It was a surprise that Boeing won, because they had so little experience in building working supersonic aircraft. I mean, they were famous for the B-52 bomber, which is subsonic. Everyone else, I mean, Convair, Lockheed had built large and fairly successful supersonic aircraft. So this was the new guy on the block suddenly being given the job, and everyone thought, can they do it?
Boeing predicted that if design and construction of prototypes began early in 1967, the first flight could be made in early 1970. The first aircraft could then be ready for airline service in mid-1974. They were talking nonsense. They had no idea of the problems they were about to face.
The main problem in designing the Boeing supersonic airliner can be summed up in one word: the weight. This thing just got fat. It got heavier and heavier. It wasn't going to make money. They had to then strip out weight, and in the end, the biggest weight penalty was going to be the mechanism to make the wings swing.
As we got beyond the preliminary design stage to build it, the weight got too heavy. The empty weight got too heavy. That was the main problem. The weight just got out of hand, and we couldn't meet the weight statement that we'd estimated for the configuration at the start.
The project slammed to a halt for a year as Boeing considered alternatives. In October 1968, Boeing emerged with what was virtually a complete redesign.
There was only one way to solve the weight penalty problem. That was to take the swing wing out.
Boeing's swing wing disappeared mostly because of the extra weight. That huge hinge in there was very, very heavy.
The 2707 was also reduced in size. Seating was reduced to 234 passengers, though that was still bigger than Concorde. And now, a new problem appeared to haunt the project and eventually kill it: the sonic boom.
We knew it existed, but frankly, I didn't think it was that bad. The sonic boom that the airplanes we were talking about was like thunder and lightning, where the thunder hits about 2 miles away. And I guess I just didn't figure it was that bad.
In order to explore the effects of the sonic boom on, for example, urban areas, the American Air Force conducted an experiment in 1964, which is something I don't think we would ever contemplate doing today. And what they wanted to do was see what effect it had on an urban area. So they they flew supersonic bombers over Oklahoma City with sonic booms or waves of shocked air passing all the time. The result was that in a very short period of time, they had around 8,000 very vocal complaints and around 5,000 complaints for claims for damages.
In 1967, immediately after Boeing had been selected to build the 2707, Dr. William Shurtleff, a scientist at Harvard University, organized the Citizens League against the sonic boom.
Well, actually, there were so many technical and economic hurdles that had to be addressed for an airplane like this, not the least of which was the sound. Reaching the sound barrier always created a shockwave over populated areas.
Well, that era was a miserable era for me, because here I was, an engineer trying to do things, and you had these idiots back there making it was a political situation, and he just dumped on it. This guy Shurtleff, I never met him. I don't know what his problem was. I know the British were taken by surprise on it. They were completely amazed at the problems we were getting.
Other scientists hypothesized that the exhaust from SSTs, expelled into the atmosphere at high altitude, would start a self-perpetuating chemical reaction that would ultimately deplete a radiation-absorbing layer of ozone in the stratosphere and bring on an increase in skin cancer.
I think there were other environmental concerns, perhaps not substantiated technically, about the ozone layer, about contamination of the upper atmosphere. There were all sorts of boogeymen shoved into the front of the table having to do with so-called environmental problems.
But public opinion was turning against the SST. And as resistance grew, Congress itself began to express doubts about the plane. In response, President Richard Nixon, shortly after he was elected in 1968, appointed a 12-member committee to report on the project.
Nixon was a firm believer in the SST when he came to power, like Presidents Johnson and Kennedy before him, and he felt that the SST was essential to American prestige. And in order to underline the case for the SST, he appointed a committee. To his great surprise, I think, and consternation, the committee came out against the SST and decided it was completely unviable.
Apart from the sonic boom, the Boeing SST was encountering other problems. When he set the goal for the American SST, President Kennedy had decreed that it would fly faster than its European rival at Mach 3. But at that speed, an aircraft's skin becomes red hot. You have to make it of expensive materials that will not melt or crack at those temperatures.
To reach the speed that the 2707 was going to go at, you had to find new materials to deal with the buildup of heat. The most effective material would be titanium. And at that time, titanium was really, really complex to machine, very expensive to get a hold of. It was going to make the whole project uncommercial.
It's tough environment, and temperatures in Maine is a real big problem. Whether you can ever design a structure to meet all this and still have enough left over to make any money with is not too clear at this point.
The British had long since decided that these problems were too difficult and expensive to bother solving. Concorde would fly at less than 2,000 kilometers per hour, where the heating problems were much reduced. Concorde could therefore be built out of standard metal alloys to keep the manufacturing costs down.
You went much faster than Mach 2. We got too hot for aluminum. I don't know. Aluminum, I can't tell you exactly, but you wouldn't want to go too much beyond 2 to get to with aluminum. So you needed a better material. And titanium was quite capable. It was a good material, and we felt that it would be. So part of the program was learning how to manufacture.
As Boeing's engineers grappled with the problems, the 2707 program suffered delay after delay, while costs skyrocketed.
We spent several $1 million of our own company money in working titanium on the side of the outside of the contract on the SST, but maybe we were too ambitious. It might have worked at 2.5 Mach number, but I think that you go 3 and that's 400 degrees, and that's too hot.
On May the 18th, 1971, the United States Senate met to vote on a motion to end funding the SST project. President Nixon had worked hard to persuade the senators to keep on with the project, but without success. The Senate voted 58-37 to kill the Boeing 2707.
I think that Kennedy's decree that the SST should be bigger, better, and faster than the European rival did cause major problems for Boeing and for the whole project right throughout it, because they were always aiming for this kind of Kennedy standard of Mach 3 and all the problems that are associated with flying at Mach 3.
I think that was too hard. It just wasn't practical. I think we could go faster than the 2. I think 2.5 would have probably been okay from a temperature standpoint, but certainly any higher than that would have probably not been practical.
Europe looked like it had won the technological race. In 1973, only 18 months after the Boeing SST project was cancelled, Concorde made its first visit to the USA to attend the inauguration of the new Dallas-Fort Worth airport. During its 4-day stay in Texas, Concorde made supersonic demonstration flights over the Gulf of Mexico and proved to be the outstanding attraction in the flying displays, which formed part of the airport dedication ceremonies. But it would soon become clear that Concorde's victory was no victory at all. The problems that beset the Boeing 2707 and eventually killed it also affected Concorde, particularly the sonic boom. British Airways flew its first ever regular supersonic flight between London and Bahrain in the Persian Gulf on the 21st of January 1976. Unfortunately, the route was mainly overland, forcing Concorde to fly at subsonic speeds on large portions of the flight. Next came the introduction of a service to Singapore. That on the 13th of December 1977, after only 3 return flights, service was suspended because of complaints from the Malaysian government about the supersonic boom over the Straits of Malacca on the west coast of Malaysia.
Ultimately, Concorde, though it made it into passenger service, it suffered the sonic boom problem that had dogged the early Boeing project. The Americans banned supersonic flight over the continental United States. Some people said that was in retaliation. Whether it was or wasn't is neither here nor there. It meant that Concorde could only fly supersonic over the Atlantic.
It couldn't meet any of the requirements that we couldn't meet. They don't meet the sonic boom, and they don't meet the takeoff noise, and I guess there are probably only half a dozen or so flying in each airline.
Concorde will never be profitable in the sense of making back the money that it costs to buy or to develop. As far as the airlines are concerned, well, Concorde makes money on an individual flight-by-flight basis because it can charge very high tickets to the kind of luxury passengers that are there.
The system exists now because it's unique and it's high cost and it's one of a kind. And if you want to make a splash, you go over on the Concorde. And okay, Betsy and I were on that one. We went over. Took off from Washington about 4:30 we took off from Washington about 4:30 in the afternoon in a hotel room in London, 9 o'clock. It's great.
But there is one aspect of the Boeing 2707 story that has never been told. A development that was to usher in the age of airline travel for everyone. On December the 22nd, 1965, Boeing's chairman, William Allen, and Juan Trippe of Pan American Airways signed a letter of intent which committed Pan Am to purchasing 25 of a new cargo plane. Unlike the 2707 that was dominating Boeing's attention, the new plane was almost an afterthought. Boeing kept it simple. The design was just a scaled-up 707. They called it the Model 747. The world would call it the Jumbo Jet.
The 747 is an amazing story. And it started back right after the Vietnam War, where the government said, we need to move a lot of material and a lot of people around the world in a hurry.
The 747 was actually developed in tandem with the Boeing supersonic project. And the aim was to put in the 747 what you couldn't get in the supersonic aircraft, which was freight. It was just meant to be a big cargo plane in the first place.
The Boeing company in 1965 decided to scale up the 707, I think as a freighter originally, but soon realized you could pack so many people into these aircraft and fly them at high subsonic speeds that it was very, very commercially viable. It made great sense.
When the dream of supersonic passenger flight died, there was only one plane to step into the breach, the 747. The first 747 entered service with Pan Am in 1970 and started a true revolution in flying. Suddenly, the cost of long-distance air travel was within the budget of the ordinary family. The age of mass air transport was born.
I think the 747 will still be flying in 20 years. It's one of the major developments of this century in aerospace.
Curiously, there's one hangover from the old supersonic project that ended up in the 747, and that was seating arrangement. When they transformed the 747, the jumbo jet, into a passenger plane, because it was wide-bodied, they could put in a couple of rows, you'd get a lot more seats. And that was the original dream that the supersonic transport had been born with.
But Boeing's interest in supersonic passenger flight did not end with the 2707. In Russia, NASA found a mothballed example of the Soviet SST, the Tu-144, nicknamed the Concordesky.
The Russian SST actually flew just a few months before Concorde. And when people saw it, they said, gosh, that looks like Concorde. And that's because, of course, the Russians had stolen, line for line, page for page, the plans of the Concorde and built it themselves.
But the Concordesky never entered international service. Soviet technical know-how was not up to the challenge of building a supersonic airliner, not even with the help of stolen plans. The plane proved difficult to fly and fundamentally unsafe. Its last outing was as a flying laboratory to try and solve the environmental problems that had plagued the old 2707. Engineers from NASA and Boeing envisioned a new supersonic jet that could fly 300 passengers at more than 2,400 kilometers per hour and cross the Pacific from Los Angeles to Tokyo in a mere 4.5 hours. But that was precisely the specification the old 2707 cancelled nearly 20 years earlier.
The main thing that's happened is you've gone to high bypass ratio engines, and the engine cycles changed, and the noise problem isn't as bad as it used to be with a pure jet.
20 years had brought more knowledge about building and flying complex supersonic machines. But the same old problems still stood in the way. A big supersonic craft designed to fly beyond the heat barrier would be incredibly costly to build, fly, and maintain. And there would still be pollution and noise.
There is no technology anywhere that I'm aware of that says that you can bypass, overpass, whatever, the supersonic barrier. It's there. The boom just has to be there. There's so much energy involved when you go through that barrier.
The dream of supersonic transport was an engineer's dream, it was a politician's dream, it was Kennedy's dream. The passengers wanted something different. They wanted cheap tickets, they wanted reliable service, they wanted comfort, and that will always be the future of the airline business.
Now, as a matter of fact, if somebody were to ask me today, will there ever be a supersonic airplane in the U.S., built by the U.S., I would say first you got to define what you mean by supersonic. There may very well be a more advanced Mach 2 airplane, larger, more economical, and so forth than the Concorde. They may very well be, I don't know that. But we are still today not ready in materials to go to Mach 3. We just don't have the wherewithal to do it.
But the dream lives on. Even today, Boeing are still working on designs to push the frontiers of speed for passenger aircraft. The Lockheed SR-71 Blackbird flies at Mach 3. It is made of titanium, and metallurgy and materials technology are advancing all the time. Will the 21st century see the dream come true? This is the challenge and the true legacy of the Boeing 2707. If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.
We are all aware of the world's population explosion. By 1980, there will be 70 million more Americans. As population goes up, average age goes down, creating a younger society, better educated, travel-minded, air-minded. Today's air transportation capacity is hard-pressed to keep abreast of demand. And yet, present trends indicate 3 times as many passengers and 4 times as much cargo will be transported by air. The and profits of the future will go to those who plan ahead now. In the international contest now underway to capture the market for a supersonic airliner, the British, French, and Russians will have flown their supersonic transports years before the United States SST airborne. The Anglo-French Concorde is the major threat to both the health of our aviation industry and our national prestige. By using this plane, foreign airlines might capture revenue now enjoyed by U.S. This could accelerate an already unfavorable direction of gold flow. And yet, if U.S. airlines try to retain this market by buying more Concorde, the U.S. Treasury could sustain an even greater gold flow loss. Let's take a Concorde. It is an aluminum airplane designed to cruise at 1,450 miles per hour. It can carry about 130 passengers on a 3,800-mile flight. Although during service later, the U.S. entry, built of titanium, will be faster and more productive for the world's airline. An airplane that could have a $17 billion favorable impact on international gold flow with the minimum expected sales of 5 U.S. SST. In the field of international commerce, $17 billion would purchase 2,300 ships for our merchant marine. 1 U.S. SST sold abroad would offset the import of 20,000 foreign cars in international balance of payment, or would enable us to buy 400,000 Italian silk suits, or 10 million Japanese transistor radios. United States industry alone is not in a position to compete with the foreign governments which are fully subsidizing the Concorde and the Russian Tu-144. Therefore, the U.S. government is working in partnership with American industry to develop our SST. The government will be repaid all invested funds, plus a return of $1 billion on the minimum expected sale of 500 U.S. SSTs. It is unknown if commercial supersonic flight will be permitted over populated areas because of the sonic boom. For this reason, the economizability of our SST program is based on flying at supersonic speed only over the ocean. At least 500 U.S. SSTs will be needed for these overwater air routes alone. Meanwhile, research is continuing with the intent of understanding and reducing the sonic boom. As Boeing and General Electric move into production, many benefits will accrue to the nation's economy. Continuity of employment within these companies and their subcontractors ensure the availability of a vital portion of the nation's manpower and mind power. By production decision time, Boeing and GE will have thousands of skilled design engineers assigned to this task, and many more thousands of skilled craftsmen available. A nationwide subcontracting team is ready to move, creating an economic effect throughout nearly every state of the Union. About 50% of the total dollar outlay will go to hundreds of large and small businesses handling and processing of raw materials, supplying components, parts, and replacement items, and employing more than 250,000 American workers at all levels in all sectors of the economy. The U.S. SST means more than a stable employment for these thousands of American men and women. As SST dollars are spent and respent, billions will be circulated throughout the nation's economy, providing seed money to keep the country growing, providing economic muscle, support programs of high national priority, such as national defense and scientific research and development, urban renewal, social progress, improved transportation. For airline passengers, the U.S. SST's acceleration in speed and service will allow for better use of time. Cargo will move farther, more economically. Tightening schedules, quickening response, tapping new markets, expanding others on international routes. Non-business travelers attracted by the new ease, comfort, and speed venture into the air for the first time or extend the range of their recreational destination. Thanks to our SST's greater speed, no country will be more than a half day away. Out of this increasing flow of airborne activities will come jobs for more people, airline personnel, cargo handlers, surface transportation operators, and the multitude of other businesses and services catering to a nation on the move. The United States SST is more than the effective means of transportation for people and products. It is a symbol of America's strength, of her determination to maintain a dominant position in the world's skyway. Today, 4 commercial jet airliners operating in the free world were built in the United States. It is this important American-led market that the British, French, and Russians hope to penetrate with their transport. But this threat to U.S. leadership in commercial aviation is being met by a nationwide government industry team that is hard at work, keeping America first in the air.
Aviation, the art of aeronautics, began with the dreamers, inventors, and daredevils who dared to defy gravity. The journey of aviation was nurtured by pioneers like the Wright brothers, whose first flight marked a historic milestone. The role of aircrafts in world wars was groundbreaking, dramatically changing warfare strategies. This initiated a technological evolution in aviation, transforming the simplistic wings of a biplane into the thunderous roar of jet engines. Let's journey through the ages of aviation. Behind every great aircraft, there were great minds. These visionaries, like Sir Frank Whittle, the innovator of the turbojet engine, redefined air travel. Then there's Skunk Works' Kelly Johnson, the genius behind the SR-71 Blackbird. His designs combined speed, stealth, and power, crafting machines that dominated the heavens. The contributions of these pioneers have left an indelible mark on the canvas of aviation, shaping the course of history and inspiring generations of engineers and aviators. Each epoch in aviation history gave birth to extraordinary aircrafts, each with their own unique features and roles. The Lockheed SR-71 Blackbird was a marvel of speed and stealth. The F-105 Thunderchief, a supersonic fighter bomber, was vital in the Vietnam War. The P-51 Mustang, a long-range fighter, was critical in World War II. The P-47 Thunderbolt, a heavyweight fighter, was used extensively in the same war. The A-10 Thunderbolt II, the Warthog, is a close air support icon. The Messerschmitt Me-262 marked a leap forward in aviation technology. Each of these game changers were instrumental in their eras, and their legacies still resonate today. Beyond the game changers, there are those that have transcended their practical roles to become icons. The Concorde was not just an aircraft, it was a supersonic symbol of luxury and speed. The B-52 Stratofortesss, a strategic bomber, is an icon of power and resilience. These magnificent machines and others like them have become much more than just aircrafts. They are enduring icons that encapsulate the audacious spirit, the relentless innovation, and the boundless ambition that define the world of aviation. For more amazing aerial footage, and to join us in this incredible journey, check out the Dronescapes YouTube channel.
If you enjoyed this video, please remember to like and subscribe. And as always, thank you for watching.